Learn how to create your very own programming language. And the only prerequisite knowledge is basic Python. Aryaan Hegde teaches this course. Along the way, you'll learn more about object-oriented programming, linear data structures, binary trees, recursion, tokenization, parsing, and more. So, let's get started.
Welcome to this brand new course where I'll be teaching you how you can create your own programming language using Python. Now, the goal of this project was to teach you how you can implement a bunch of programming concepts into a real-world project. I have always felt that, especially in computer science, concepts have been taught in a sort of abstract and detached manner, independent from the real world. And that's why in this course, I bring to you a bunch of concepts like data structures, like algorithms, recursion, object-oriented programming. I teach how you can implement all of these concepts into a real-world project. You can also head over to blog.algolearn.net or click on the link in the description where I talk about a bunch of learning methods I employ during my learning phase to have a better grasp on concepts and a higher memory retention. Now, the only prerequisite for this course is basic Python knowledge, stuff like if statements, variables, while loops, and functions. And with the basic foundations laid, I'll take you to the next level, talking about data structures, algorithms, recursion, and much more. And by the end of this course, you'll have your own programming language.
So by the end of this project, we'll be having the final output. So this is I've run the shell.py file over here. And this is what our output is going to look like. So we're going to input our shadow script code as a Python input. So I'm going to say, let's say we can give an input arithmetic expression. So 1 plus 1, it returns 2. I can do 5 plus 3, it will give us 8. Now I can even talk about order of operations. So I can even do 1 plus 4 multiplied by 7. In the wrong order of operations, that'll be 5 times 7, which is 35. But the correct way to do it is multiplication first. So we'll have 7 times 4, which is 28, plus 1, 29, which is what we get. If we want to make the addition, we want to give higher priority to addition, we can add a pair of parentheses, multiply by 7, and this should give us 35. So that's all about arithmetic expressions that we can give it. Apart from math, it can do other stuff as well. It can create variables. I'm going to say make variable A. And I can assign that variable to the value 10. And like how in JavaScript you have the var declaration or the let declaration, and this time we're using make. So the make will be used to create a new variable. So we create a variable called A and give it the value 10. I can make another variable B, set it to 15, and I can make another variable C and set it to A plus B. And this stores the variables and their corresponding values in a Python dictionary. Now, after variables, we can also deal with conditional operators and comparison operators. So, Boolean operators and comparison operators. So, Boolean operators is something like stuff like and, or, and not. The comparison operators are greater than, less than, is one thing equal to another thing, and so on. So, I can run a Boolean operation. I can say 7 greater than 2 and 5 greater than 3. In this case, both of the expressions 7 greater than 2 and 5 greater than 3 both are true, and therefore this should return 1, which stands for true. If I do 7 greater than 2 and 5 less than 3, this will return 0, which stands for false. I can do 7 greater than 2 or 5 less than 3, which will give me 1 again. I can do not, so I can say not 7 greater than 2. So this will give me 0 because 7 is greater than 2, and then we're notting that operation, we're inverting it, we're turning 1 to 0. So that's the Boolean operators. We can even check if two things are the same. I can check if C is equal to B. So this is how I use it. In Python, you have two equal symbols to check if one variable is equal to another. In our syntax, we define it as C question mark equals B. And if I run this is 0. Why? Because 25 is not equal to 15. I can make another variable D, set it to 25. And now if I do D equals to C, this will give us 1. So that's the comparison operators. I can even check if C is greater than A, and that gives us 1, and so on. So apart from the comparison operators, you can now use if statements. So I can say if a is greater than 3, do something. So do 3 times 3. That makes no sense, but let's just see if this works. And that will give us the output 9 because a is greater than 3. But if I do if a is less than 3, do 3 times 3, it will give me nothing. I can also run elifs. So I can do if a is less than 3, do 3 times 3. Elif is greater than 12, do 5 times 5. Else do 10 times 6. So in this case, a is not greater than 3 and it is not greater than 12. So both the conditions won't be met, and it will go to the else statement and run 10 times 6, which is 60, as the output. Now the final thing that we implement in this course is while loops as well. So how do you run a while loop? I can say while a is less than 15, do, and then we have to make a statement. So do, following a statement, following the do keyword, we have to give a statement like make a equals a plus 1. So incrementing a's value by 1, and this will print the variables list in every iteration of the loop. So that's all there is to it in this course. We haven't talked about more advanced functionalities like strings or possibly even styles of programming which we could implement in our language, like object-oriented programming or functional programming. We haven't talked about those aspects because we want to keep this course simple while also learning about a lot of other computer science concepts like data structures, algorithms, and the programming paradigms, and lots of stuff. So we're going to talk about all of those concepts from a beginner level, and by the end of this course we'll have this amazing project built from scratch. So let's begin this course. So I want to start this course by talking about how computers are able to read code on a high level. Now, this is not really necessary to understand the implementation phase of this course, where we will be dealing with Python code and writing our interpreter, but I just think that this helps put things into perspective and explains how computers are able to actually do this stuff in a more physical manner. So ultimately, if you scale to the microscopic level, you'll find that computers are made of transistors, and they are indicated by the following symbol. So the two wires over here are electrodes, and in between is a material known as a semiconductor. A semiconductor typically made of silicon, or I'm not really going to go into the chemistry, but it composes of silicon, and semiconductor is a material that allows current to flow through given a certain input from the control wire. So this is the control wire. When the control wire is on, the semiconductor will allow current to flow through it. When the control wire is off, the semiconductor won't allow current to flow through it. So let's represent the states on and off using two numbers, 0 and 1, also known as binary. So when the control wire is on, the semiconductor conducts electricity, and if this, let's say, is the output, so then, and let's consider the control wire as the input. So we have input and output, and we have a way to represent data using binary. So over here, input is 1, the control wire is on, the semiconductor can conduct electricity, and it will generate the output 1. And if it is off, the output will also be off. Now, using transistors, we can generate logic gates. There are multiple ways to generate logic gates. You can use different mechanisms as well, but typically inside a computer, you'll find transistors, and transistors forming the logic gates. So how do you make a logic gate from a transistor? I'm going to start off with a simple logic gate, which is known as the NOT gate. In fact, there are 3 of them. There's the NOT, the AND, and the OR, which are the fundamental logic gates that computers use. They're also known as Boolean operators that we will be working with during this course, during the implementation. So NOT essentially reverses the input. So if the input is 1, a NOT operation turns it to 0. If the input is 0, the NOT operation turns it to 1. And this NOT gate is built from transistors. One way you can build a NOT gate is, okay, let me draw that again. You can have the output go in that way and have the control wire over here. So control wire is the input and that's the output. So over here, input and output. If the input is 1, that means current will flow in this direction. It will go down and flow in this direction. So the output will be 0. If the input is 0, the output will be 1. And what I'm drawing over here, these tables. So I don't know why that's not working. Yeah, there we go. So these tables are also known as truth tables. They're one of the first things you actually taught in computer science. Anyway, so it's just like 4 cells in an Excel sheet. Anyway, so that's what the NOT gate does. Similarly, you can construct the AND and the NOR gate using just combination of transistors. I'm not going to go into those details, but all you need to know is that the NOT gate flips the input operation. The OR gate has a different sort of truth table. For a certain input, it has 2 inputs, I1 and let's say I2, and 1 output. If both of them are on, this will be on. If one is on, it will still be on. But if both of them are off, the output will be off. So that's the OR gate. The AND gate is another logical operator. It has 2 inputs, I1 and I2, and it has an output. And only if both I1 and I2 are on will the output be on, otherwise the output will be 0. So that's the basics of AND gates, NOT gates, and OR gates. These form the fundamental logic gates. There are some other gates as well, like the XOR gate, but I'm not going to talk about them right now. These gates, instead of representing them as transistors, we represent them as their own symbol. So let me just draw their own symbol. And that's the OR gate. 3 gates, pretty simple. So how do computers perform arithmetic with these logic gates? There are 2 main functionalities we're looking for, arithmetic and memory. And once we understand both of them, I'm going to move on to the more the side of this course which is more relevant to creating your own programming language. So again, as I said, we have 2 operations to accomplish: arithmetic, which is basic algebra, or not basic algebra, basic addition, subtraction, multiplication, or division, and the memory is refers to storing data, essentially storing binary, and then we can use that binary to represent other forms of data, like for instance video or audio or whatever. So anyway, before we move on to the arithmetic, I want to talk about another gate, which is the XOR gate. I'm not going to talk about how it's formed. This is its symbol. It's similar to the OR gate actually, and that's not, yeah, there we go. So that's how the XOR gate looks like, and it looks similar to the OR gate. It too has 2 inputs, I2 and I1, and the truth table. And the truth table is something like this. If both are 0, the output is 0. If either one of them is on, the output is on or 1. And if both of them are 1, the output is 0. That's the XOR gate. Now, in binary, you can also perform addition. So what I was referring to as arithmetic. Let's say you want to add the binary numbers 1 and 1. So you would have to represent them as 1, 0. Essentially, how you represent binary numbers is the following way. You represent decimal numbers, which is the base 10 notation, in the form of powers of 10. So for instance, 10 to the power 0, 10 to the power 1, 10 to the power 2, and so on. So that's the ones position, tens and hundreds position, and so on, that we've been learning in elementary school. So if you have, let's say, the number 3, 4, 6, so that just corresponds to 3 times 10 to the power 0 plus 4 times 10 to the power 1 plus 6 times 10 to the power 2, which is 643. So that's how you represent decimal numbers, but binary is different. It is base 2. So you have 2 to the power 0, 2 to the power 1, and 2 squared. And you can't have numbers from 0 to 9. It's not base 10. You can have numbers only from 0 and 1, so 0 and 1. So if you want to represent the number 3, let's say, so that'll be 0 over here, 1 over here. No, wait, it'll be 1 over here, 1 over here, and 0 over here. So 0, 1, 1 is 3. How so? Let's do that. So it's 1 times 10 to the power 0 plus 1 times 10 to the power 1 plus 0 times 2 to the power 2, and this turns out to be 3. So that's how you do basic addition in binary. So that's how you do basic addition in binary. Now, if you look at the XOR gate, the truth table of the XOR gate, it actually looks pretty similar to our addition. So I'm going to do addition for 1-bit numbers only, just to demonstrate the idea of arithmetic using logic gates. So I'm going to do 0 plus 0, which is 0, 0 plus 1, which is 0, 1 plus 0, which is 1. Okay, and the previous one is also 1. And 1 plus 1, as I said, it's not going to be 2, it's going to be 1, 0. And 1, 0 essentially refers to the fact that it's 2 to the power 0 and 2 to the power 1. So you have a 0 over here and 1 over here. So that's just 2 to the power 1 times 1, which is 2. And 1, 0 equals 2 in decimal. So now if you look at this over here, you can see that the sum, which is the first number, is exactly the same as the XOR gate. It's 0, 1, 1, 0, 0, 1, 1, 0. But the carry bit, which is this one over here, that's called the carry bit because it becomes like in decimal addition, you take 1 as the carry. So you take 1 over here and then that comes down over here as 1. So the carry bit is one that we have to find another gate for the carry bit. The carry bit is 0 in these cases, but 1 over here. And that's the situation for the AND gate. So if you can combine the OR gate, the XOR gate, and the AND gate, you can actually come up with a way to handle addition in using logic gates only. And that's essentially how we go. That's the starting point. You go from there, try to handle more complicated arithmetic like multiplication or division. And that's the same basic idea. You are trying to hook up logic gates in a smart manner to perform calculations. And that's how arithmetic works in computers. So now let's talk about memory. I'll be using a component called the AND OR latch as an example to show how computers have the ability to store data. So it's called the AND OR latch, as I said. So let me just construct it. So R stands for reset, S stands for set, and O is the output. So we use the set wire to save data. So if you want to save the binary number 1, or just want to save the bit 1. So how do we do that? So the first thing we need to do is turn on the set wire. So I'm going to draw a truth table over here. So we have set, reset, and let's not worry about reset for now, and output. So if you put set as 1 and reset as 0, what will happen to the output? So this is an OR gate over here. So on OR gate, so once you turn on the set wire, 1 gets transmitted over here, because if either of the inputs of the OR gate are 1, the output of the OR gate is 1. So the output of the OR gate is 1 over here, and the reset is 0, so 0 gets knotted, and that becomes 1. So now the AND gate converts these two input 1s into the output 1. So in the following scenario where you turn on the set wire and leave this reset wire as it is, the output turns out to be 1. Now afterwards, if we turn off the set wire, let's turn off the set wire. So let's make it 0, and the reset wire is still 0. What will happen to the output? So now the set wire is 0, but regardless, since the output was 1 and that was fed back as an input to the OR gate, this is 1 over here. And since one of the inputs is 1 to the OR gate, this still remains as 1. The input to the AND gate, the bottom input to the AND gate still remains as 1, and therefore the output still remains as 1. So the output is effectively unchanged even after we turned off the set wire. And that is effectively what computer memory looks like. So the computer has remembered the state it was in, and that is known as saving or computer memory. You can delete it by turning on the reset key, and that's also pretty easy to follow. If we turn on the reset key, that gets knotted to 0, and one of the inputs of the AND gates becomes 0, and the output becomes 0, and we are back to our original state. So that's how basically computers store memory. It's sort of this feedback mechanism that they use that helps them store memory. And now that we've understood these two concepts, let's go ahead to the next section where we will talk about the need for programming and why we need to use programming languages. So what is the need for programming? That's what we're going to talk about in this section of the course. Now, programming refers to giving input instructions to a computer so that it can execute them. So before we understand how programming works, we have to understand how computers understand instructions. That's a mouthful. Let me say that again. To understand how programming works, we need to understand how computers interpret instructions. And as I said all along, that they do this using logic gates. So we have a set of logic gates hooked up in a smart way so that they can detect certain instructions. Like for instance, if we have the instruction 1000, so that's the 4-bit instruction over here. Now, how do we decode this? The computer has a control unit which is responsible for checking for certain instructions, looking for certain instructions, and once it finds those instructions, it will perform the necessary action. So that's how computers interpret instructions. They have a control unit. Control units compose of logic gates. So let me just say you have the instruction like this. So this is the instruction. It's fed into control unit, and the control unit detects the instruction, checks if say for instance the instruction 100 corresponds to adding to memory, let's say. So the control unit will check for that instruction. If the instruction is 100, and again these instructions are stored in the memory of the computer. We talked about how computers save things. So the instructions are stored in the memory of the computer. So once it sequentially goes through all of the instructions stored in the memory, and let's say this is the instruction it first encounters, and it tries to match it with the instruction 1000, and let's say in the situation where it does match with this number, let's say the instruction is 1000. In that case, the control unit will detect it using logic gates, and once it has detected that instruction, it will go ahead and perform the operation of saving to memory. So there's two stages: detecting the instruction using the control unit, and then performing the instruction. So you have a table like corresponding to 1000 corresponds to saving to memory, maybe 0100 corresponds to doing arithmetic, adding two numbers, let's say. So you have a table of these instructions. So you first design these instructions, and then programmers will go ahead and input these instructions into the computer's memory. The computer would sequentially perform each instruction and will execute them. So this is how computing works on a really high level. And the problem arose, and this is in the early ages of computing, the problem which arose was that you used harder mediums, which is like hardware interactions, to input data. These instructions like 100 were fed in by mechanisms like switches or plug boards, or you had some punch cards. So these harder mechanisms are not really effective, especially if you have thousands of instructions to give to the computer. And that resulted in the need for a softer way, a softer medium for interacting with a computer, and that gave birth to a compiler. A compiler converts, you have high level source code, which is essentially a programming language like Python, and that source code is written in such a way that it's human readable. And you have a compiler, which is just another computer, which uses a set of techniques to convert that source code into binary, which is also known as a machine code. So that's the job of a compiler. It converts source code into machine code. And in this entire course, we'll be learning about a lot of processes that compilers use to convert to machine code, namely lexical analysis and parsing and interpretation. We won't be building a compiler, we'll be building an interpreter. So we won't be dealing with converting the instructions into binary outputs. Rather, we'll be using a programming language like Python to convert to interpret data in a sequence, to interpret our own programming language sequentially. So a compiler converts to machine code, but our interpreter won't be doing that. It will be using a programming language like Python to understand our given input and then process it and perform the necessary action. So anyway, that's it for this section. We've talked about how computers understand instructions, how they execute those instructions, and the need for compilers to convert high-level code to low-level code, and those low-level codes is just binary instructions. And now with that information, it's time to move ahead to the next section where we will be delving more into the implementation side of this course. So I'll see you over there. In our interpretation process, there are 3 steps involved. The first step is known as lexical analysis. And then after that, you go ahead and do parsing. And the final stage is the interpretation, which is done by the interpreter. So 3 steps, and if you encapsulate these 3 steps into its own box. So I have an interpreter over here, and that box is called an interpreter. And if I input some code, which is in our custom programming language, and for the purposes of this course, this programming language will be called ShadowScript, which is a fancy name for a not so capable language, because of course we won't be able to achieve tasks that advanced programming languages like Python or JavaScript can do. But nonetheless, we'll be talking about the core functionalities like variables, like arithmetic operations, some if statements, while loops, and possibly even for loops. So all of that code will be implemented. It won't be as powerful as the modern programming languages, but still it's a great opportunity to learn lots of programming concepts. So anyway, this interpreter will take high level code, and in our programming language it will take ShadowScript in it. So it will ingest ShadowScript and spit out the necessary actions, the necessary output. Like say for instance you're creating variables, it will spit out the value of the variable and save the variable. If you want to do some arithmetic operations, it will do the arithmetic for you and spit out the output and so on. So it'll just give an output, and it may also deal with some of the memory processes like saving new variables, deleting variables, and all of that. So it produces an output which will be visible on the shell, on the terminal, and it will also be dealing with some memory changes. So it's these 3 steps that okay, I don't know what happened over here. Let's just fix that. So it's these 3 steps that we have to talk about, because this is what goes on inside the black box. And the first step is lexical analysis. So I'm going to create a new page for this one. And this is known as lexical analysis. The process is pretty straightforward, easier than the other steps, and it involves just breaking down the input code into specific tokens. Now, the tokens for our purposes can have a value and also a type. Like for instance, the number 5 has a value of 5, and so that's its value and a type of integer. The plus operator has a value of plus and it's a type of operator, so op. So the lexical analysis just breaks down the input into tokens, and that's pretty much it. That's all it does. And in the next stage, we'll feed the tokens as an input to the parsing. So the input of the lexical analysis is the original code. The output produced from lexical analysis will go to the parser, and the output of the parser will go to the interpreter, and the interpreter will give the final output. So lexical analysis, you give an input, and I'm gonna call it tokenization because lexical analysis is pretty hard to say, and they mean the same thing. So yeah, so tokenization, you give an input, which is the shadow script code. So tokenization, and it will break down the input code into specific tokens. And in our case, it will store those tokens in a Python list. I'll talk about data structures in just a few moments, but probably in the next few sections. But just know that it will store the tokens in a sequential way in a list. So a list is just like a traditional list, token 1, token 2, and so on. So that's a list, and this is the first item of the list, this is the second item of the list, and that's how a Python list looks like. Now, to give an example, let's say the input is the arithmetic operation 1 plus 3. So we want to add the numbers 1 and 3. So after the tokenization process, the output should look something like this. It should store the token value of 1 and of type integer. Then it should store the token, okay, let's put it below. So first it'll store token 1 and it'll be a type integer. Then it will store a token, the plus symbol or add symbol, and that's an operator, and so on. And the third final one is the third token, which represents the integer 3. So that's the output of the lexical analysis stage. And now let's go to the next section where we will talk about how we process these tokens, this stream of tokens, how we process them. So the next step is called parsing. So from the tokenization process, we have received a bunch of tokens stored in a Python list, and now we have to process that list and generate a useful output. So what is parsing? First of all, let's understand the definition of parsing. And fundamentally, parsing is just the recognition of patterns in an input. Like say, for instance, we have the input 1 plus 1. And in a very simplistic interpreter for our programming language, we can interpret this expression by first tokenizing it. So we tokenize this into a bunch of tokens. We have the number 1, then we have the plus symbol, and then we have the number 1 again. And now once we have these tokens in a list, in the parsing process, we look for a pattern. In a simplistic way, let's say the interpreter can process only the addition or subtraction of 2 singular digit numbers, like for instance 1 plus 1 or 3 plus 4 or 5 plus 6 or something like that. In this case, the pattern that the parser has to recognize is that the first number is an integer. The pattern that the interpreter has to recognize is the first number is an integer, or the first token is an integer. The second token is an operator, and the operator could be plus or minus. And the third token is again another integer. That's all that the parser has to recognize in this simplistic scenario. There's an integer plus or minus another integer. And the parser just remember the lexical analysis, the tokenization process blindly converts the input into a bunch of tokens. It does not look at any structure. It does not see if the input abides by the programming language rules. It doesn't do anything like that. All it does is converts the input into a bunch of tokens. But in the parser, it tries to search for patterns. It tries to search for this pattern of integer, integer plus integer. So that's the general pattern. So integer plus or minus, and this vertical bar is also known as or. So plus or minus another integer. So that's the pattern that we're trying to look for in this simplistic scenario. Of course, this is not how our parsing process will be in the implementation side. We will be able to deal with extremely complicated expressions as well. But this is just to give an example of what parsing really is. All it is trying to find structure, and essentially it goes a step further from the lexical analysis and tries to structurize the input. How does it do that? And it does this using a bunch of grammar rules. Now, in this simple scenario, the only grammar rule is that an expression is an integer plus or minus another integer. In fact, I'll write this in a better way. So it's an integer plus an integer, integer minus an integer, and the vertical bar here. So either this is one possibility or this is the other possibility. So in this simple grammar rule, and this layout is known as a grammar rule. There are certain formats of writing a grammar rule, and I'll come to that in just a second. But this grammar rule essentially defines the structure of our programming language. The parser checks for certain patterns, checks for such structures, and sees if the input matches for them. If it does not match them, then there's probably an error in the input code and an error must be raised. So let's now talk about the types of grammar rules that exist. So the ways in which you can write grammar rules. The one I'm going to use is called BNF, and that's extremely hard to pronounce, but it's called Backus Nor form, I believe, and I probably mispronounced that. But anyway, BNF is a way of writing your grammar rules, and let's just go through a bunch of examples. Now, in basic math, we have, let's say, an expression. An expression just contains a bunch of terms, and a term is just a bunch of integers multiplied together. So what does that mean? So let me go through this again. I'm going to say an expression is equal to, and in Backus Now form, you actually have 2 colons over here, like that. But I'm just going to write it as 1 colon because it looks much more prettier. So like that. Expression is equal to a term plus another expression, or it's equal to a term minus another expression, or it's equal to just a term. Now, this may seem a bit confusing because we're calling the expression inside the expression, but what this tries to do is just ensure that there is a form of continuity in our expression. What does that mean? So let's say we have the expression 5 plus 3 plus 2. Now that's an expression. It's a combination of terms, and a term can be an integer, or it can also be 2 integers multiplied or divided. But I'll come to that in just a second. For now, let's just assume a term is an integer. So an expression just contains a bunch of integers added or subtracted together. Now, this is where recursion comes into play, and I'll talk about recursion in probably the next few sections. But essentially, recursion is a type of programming where you're calling the function or certain functionality within the functionality. So as you can see over here, we call the expression inside the expression itself. So what this tries to do is that it tries to ensure continuity. So over here, the term, let's say the first term is 5 plus another expression. Our expression can be equal to a term plus another expression. So we can say 3. So the 3 is a term, so we can have 3. Plus, now expression can be a term as well. So 2 is a term. So all we're trying to do is we're trying to ensure continuity so that we can enable multiple additions over here. So even if there are 1,000 integers added together, we can ensure that all of them are conform to the grammar rule, because this is a pretty sound and pretty grammatically correct expression. 5 plus 3 plus 2 going on for n number of terms. If you still don't understand what I mean, I'm going to use a much more easier comprehensible format. So another way to define an expression would be to say, okay, its expression is a term multiplied or divided. So you see we use the bar. In fact, I'm just going to use the symbols. So it's a term multiplied or divided by another term, like that. Now what does this mean? This means that an expression can be equal to just one term, or it can be equal to a term multiplied or divided by another term. Actually, that should be plus or minus. That's my bad. Plus or minus. So an expression can be a term by itself, but this part over here, where we are enclosing, let me just get that right. These two enclosures over here, followed by an asterisk, represents 0 or more times. That means, now let's clean up that. Yeah, that means this, the contents within that curly brace can be repeated 0 or more times. That means a term can be a term plus another term minus another term plus another term, whatever, 0 or more times. And that is effectively what the Backus-Naur form is saying. It's calling the expression within itself to tell you that, okay, an expression can contain n number of expressions. So we're using a form of recursion to tell the users, or to tell the programmers, that an expression can have n number of integers, n number of terms added or subtracted multiple times. Now let's define the term. So a term, as I said, it can be equal to just another term, or it could be equal to a term. It could be equal to a factor. Now a factor is just an integer for our purposes. So a term could be equal to a factor multiplied by another factor, or multiplied by another term. And you see I'm doing the same thing over here, recursion, and just to symbolize the same thing, as I said, the multiplication, that means the term can be equal to a factor multiplied by another factor multiplied by another factor n number of times, 0 or more times. So a term could just as well be equal to one factor. It could be equal to two factors multiplied together, three factors multiplied together, and so on. So that's what I'm trying to signify by calling the term within the term itself. So by calling term over here, I always get the arrowhead wrong for some reason. So by calling the term within the term grammar rule, I'm trying to showcase that you can have multiple factors multiplied or divided together. So as I said, a factor can be multiplied by another term, or it could be a factor divided by another term, or it could be just equal to a factor. Now, what is a factor? For now, although in the later part of this course I'll bring in another aspect to this factor definition, but for now a factor is just equal to an integer. So it could be, let's just do integer, like that. An integer is just a series of digits, but I'm not going to go ahead and define that because I'm pretty sure all of you know what an integer means. Now, in the set of grammar rules, we have some terminology as well. So the integer, although it technically isn't, and okay, let's just go ahead and do it. So I'm going to say an integer is, for now, let's just say the integer is a singular digit. So I'm going to say an integer is just a digit, 0 or 1 or 2 or 3 or 4. Right, so an integer is just a singular digit, and I'm defining that in this way just to keep things simple. As you all know, an integer can be a series of digits, like 3, 4, 5 is an integer, or 1, 2, 3 is an integer, and so on. So in this notation, in these grammar rules, what is inside the angular brackets is called a terminal. is called a non-terminal. And that essentially means that a non-terminal can be defined by using a terminal. So a terminal in this case is something like an integer, which we can concretely define like a digit. Another terminal in our programming language could be the operator, like plus or minus is another terminal. These can be concretely defined. They are the base tokens of our language. So with that knowledge of Backus-Naur form, how does all of this relate to parsing? So as I said, Backus-Naur form is a way of defining rules. Once we have defined rules, things actually get pretty simple. It seems that you're still far away from having a workable interpreter which can convert your custom programming language and execute it. It seems that we're far away from that goal, but now that we've defined our grammar rules, things get a lot more easier. So now I'm going to take an example to showcase how parsing is actually done now that we have the background knowledge of BNF and also about how parsing introduces structure. So in parsing, let's say we're trying to parse the input 1 plus, let's say 1. Now the expression, using our previous notation, we said that the expression is equal to terms added or subtracted from each other. Now a term can be equal to a factor being just an integer. So in this case, the expression is equal to 1, which is a term, plus another term, 1 plus 1, and that satisfies our grammar rule. But even if we have something complicated, let's say 3 plus 5 times 2. The grammar rule says that an expression is a term plus another expression. So essentially saying that, again, I'm repeating myself, but an expression is just a term added or subtracted from another expression n number of times, 0 or more times. So the expression over here is equal to 3. 3 is a valid term, which is equal to a factor in this case. And even 5 times 2 is a valid term, because remember we said that a term can be equal to a factor multiplied by another factor 0 or more times. So this is equal to a factor multiplied by another factor. So even this input is parsable using our given grammar rules. What do I mean by parsable? That means that it conforms to our grammar rules, and such an input can be processed in the parsing stage. Now I'm going to use a data structure known as a binary tree, which I'll talk about more extensively in the next few sections. But I'm going to introduce the binary tree to talk about parsing. Now parsing essentially involves, again, bringing structure into your code. So let's say we have the expression 1 plus 2 times 5. I'm going to construct a tree for this given input, and the tree is the following. So this tree over here, we are adding the integer 1 and we're adding the product of 2 and 5, and this is the parsed tree. In fact, the goal of the parsing process is to generate a tree like this. Of course, we won't be drawing a tree like this in Python, but we will be representing such a tree in a list. So how do we represent this tree specifically? I'm going to write it over here. So I'm going to say 1 plus 2 times 5, like so. So in this scenario, plus is the operator, 1 is the left node. In fact, this is known as the root node. I'll talk about this terminology in just a few sections. But this is the left node, and this is the right node. So over here, 1 is our left node, plus is our root node, and right node is 2 times 5. So we have effectively represented this tree using this list in Python. In this section of the course, I'll be talking about object-oriented programming and its 4 main pillars that make it, according to me at least, more superior than the other paradigms or the other ways of programming. So the first way is functional based programming, which uses pure functions, and functions is just a like similar to how a mathematical function works. You have an input, you give out an output, and that's basically it. There's some inner workings to a function. It's like a black box. You have an input, you have an output, but you don't see what's inside. So that's how functions work. And just to give an example, let's say we're trying to calculate the amount of fuel that you have left in your car. So we create a function called remaining underscore fuel, and this takes in the initial fuel that you had, the kilometers that you drove, and also the ratio, which is like the gallons per kilometer or whatever unit you're using, liters per kilometer, the ratio of that. And the remaining fuel would just then be equal to initial minus kilometers times the ratio. So in functional programming or functional based programming, you separate the data from the actual functionality. You see that we have not accepted any data like the initial fuel that he had, the kilometers that he had, or the ratio. We didn't accept any data. This is just a standalone function, a standalone functionality which can basically work fine. I mean, even if I run this right now, there'll be no problems. So it can work on its own as well. So the actual usability of it comes when we add some data. And the essence of functional based programming is that you separate the data from the functionality. So now over here I can give in some data. Let's say I say the initial fuel is equal to 50 units. The kilometers this person drove is let's say 10 units, or okay, 10 kilometers, and the ratio, let's say, is 5 units per kilometer, 5 units of fuel burnt per kilometer drove. So then I can calculate the remaining fuel. I can print it as well, remaining fuel, and I can give the parameters initial, kilometers, and ratio, and this works fine. So if I run again, this time you see we have zero, exactly zero. Let's reduce the ratio here a bit, and let's run that again. You see we have 30 units of fuel still left. So this is a pretty basic example of functions, and it seems fine in this level, but let's assume that you have a lot of complexity in your application. Let's say you're building a website and you have the authentication aspect of it, you have the payment aspect of it, you have the content management aspect of it, so many entities involved. Now, how do you declutter this mess? Because if you have so many entities involved, you'll have several functions. You'll have authentication functions, you'll have payment functions, and all of them clubbed in this messy file where it just becomes difficult to handle things. And that's where object-oriented programming comes in. Object-oriented programming divides it divides code into entities called objects. So you can have one object of payments, you can have one object of authentication, one object of content management, one object of maybe like contact or a server where you have chat functionality or something like that. I don't know. So in object-oriented programming, you divide an application into objects, these entities which have their own data and their own functionality. Now, let's try to understand how object-oriented programming works on the canvas. So, as I said, just as a recap, let's just recap what I said. In object-oriented programming, also called OOP, you divide things into their own entities called objects. So you can have maybe an object for payments. So it has its own data, it has its own functionality, but it's all enclosed in this own entity known as payment entity. We can have another entity for, let's say, authentication, which has its own set of data, its own set of functions, completely different from the payment. And you have authentication over here. And you can go on and on, but you get the point. You're encapsulating data and functionality into objects, which are the basic unit of object-oriented programming. And these objects just represent entities like payments and authentication. Now, in object-oriented programming and inside an object, the data is referred to as properties and the functions are referred to as methods. So now that we've understood the basic gist of object-oriented programming, let's try and understand what are the four main pillars that hold it and make it such a solid way of writing your code. So the first main pillar of object-oriented programming is known as encapsulation, and it's the basic idea we talked about in the previous section. Encapsulation refers to basically just that, encapsulating properties or encapsulating data and functionality into their own entities so that we can better handle them, and it just enables us to write more cleaner code. So as an example of our own situation over here, we have multiple entities. We have the Lexer, we have the Parser, we have the interpreter. So it seems wise to use object-oriented programming because it can encapsulate each of these entities and have designate them their own properties, their own methods, their own data, their own functionality. So we can have a Lexer, which has its own data, its own functions or methods. I'll call it functions for now because, yeah. So the data is known as properties, and functions in object-oriented programming is called are called methods. So this is one object. You can have another object. You can have a parser, which has its own data, its own functions. And you get the idea. We can have a similar class for the interpreter. This is called encapsulation, by your grouping things, grouping data, and grouping functionality. The second pillar is known as abstraction. And abstraction just refers to simplifying the inner functionality, basically just that, the inner functionality into its own entity. Like for instance, in our situation over here, all we need to do in object-oriented programming is create a Lexer, which is of the object Lexer, and let's say we tell it to tokenize stuff using the methods. So this is some notation which I'll go over in just the next section, but all this is doing is creating an object called Lexer, and it's tokenizing the inputs, the input expression. So as you can see, this is a very clean way of writing code, because essentially you're just abstracting away the inner complexities and the inner functionality of the Lexer. All you're doing is calling the tokenize method, and you have your tokens ready. All you're doing is calling the Lexer object, and you have your own Lexer. So that is known as abstraction. It allows for code reusability, it allows for modularity, and essentially if you have different developers working on different tasks and they really don't know how the other developer is coding his stuff, so they can use object-oriented programming to communicate. They can say, okay, this is one component, this component will give a certain output. You don't need to know how it works inside, it's a black box. You don't need to know how it works on the inside, but all you need to know is for a given input you're getting this output. So that's what abstraction is, abstracting away the complexities, making code look simple. And let's move on now to the third pillar. The third pillar of object-oriented programming is known as inheritance. Inheritance is a concept that is best explained by an example. So let's say we are creating a website, and each website has different components. It has the home page, the about page, and the home page has different contents in it. The about page has different contents in it. But if you're designing a website, you typically would have the same layout for each page. You'd have the heading, you'd have the body in pretty much similar positions. So inheritance in object-oriented programming allows you to inherit certain common properties within objects. So what do I mean by this? Let's say we have an object called page. It has properties like heading, body, and the images maybe. So this is the base class. This is what you are inheriting from. Whereas you have maybe another class like the home class, which is the home page, or the about class, which is the about page. And these classes will inherit all of these properties. The heading, all of these will be inherited by the home object. And yeah, so again, the home object would inherit the properties and the functions of the page object while having its own custom functionality which it will add over the page object. So that's basically what inheritance is. You have a fundamental object and other specific, yeah, implementations of it, like the home page, the about page, inheriting from that fundamental object. This is a theoretical discussion here. I hope you understand what inheritance means in a more theoretical sense. In this course, I'll be doing object-oriented programming in Python. So I'll be talking about how you implement inheritance and all of that as well. And with that knowledge, let's move on to the final and fourth pillar, which is known as polymorphism. So the fourth main pillar in object-oriented programming is known as polymorphism. And polymorphism is essentially the idea that you can treat objects of different types as if they were the same type. So that may sound a bit confusing, but I'll explain it using an example. So let's say we have three types of animals. We have dogs, we have cats, and we have birds. Now the common thing about all of these animals is that they can make a sound. So how can we program a way in which how can we program the sounds of these animals? So maybe for the dog we do make dog sound. So this is what you would typically do. But now in polymorphism, the idea of polymorphism is that you can make a common interface. Now in this instance, the common interface would be an animal. All of these three entities are a type of animal. So the common interface over here, I can define it to be an animal. And what polymorphism allows you to do is, let's say we create a method in animal called makeSound. And now using this common interface, you can add some custom functionality to this makeSound method. So maybe the dog does a woof upon the makeSound method, the cat does a meow on the makeSound method, and the bird does a chirp on the makeSound method, whatever. But polymorphism allows you to call the same functionality of the dog and the cat and the bird using the same method, but each of these entities, dog, cat, and bird, do it in their own customized way. And that's the idea of polymorphism, which means many forms. It's the idea that you can allow objects of different types to be treated as if they were the same type based on a common interface, and the common interface being the animal. So that's the idea of polymorphism. And with that, let's move on to the next section. In this section of the course, we will be talking about the Python implementation of object-oriented programming. Now, we've talked about the theoretical aspects of object-oriented programming in the previous sections, where we talked about objects, how objects define a certain entity, and we group a set of functionality, a set of properties into each object, and we separate them using object-oriented programming. So how do you define an object? How do you define one entity? Like, as I said previously, we can have a payment entity, we can have an authentication entity, we can have, I don't know, let's say contact page, or let's do chat entity in the example of creating a website. So let's say we're creating a website. All three of these are their own entities. So how do we create these entities in Python? How do we create these objects in Python? Now, to create an object, we must use the keyword called class. A class essentially defines a blueprint for each object. So as you might know, the payment will have different set of functions, authentication will have different set of functions, the payment will have different set of input parameters. It might have the user, it might have the amount of payment, the recipient, the donator. The authentication will have different parameters. It will have maybe the username, the password, the ID, or the email address, the chat will have different input parameters. So because we have different input parameters, different functionality for each entity, we must define a blueprint for each entity. So let's say we create a class for payment. Now, as I said, each entity will have different set of input parameters. Like payment will have the input parameter payment, recipient, amount, and all of that. And it will have a different set of functionality, maybe to process the payment. Authentication will have a different set of functionality, maybe to check if the password is correct or something like that. So we can take in the input parameters for each class using the init method. It's a special method, and this init method works in a way that you can take in the self parameter over here. Now I'll talk about self in just a second. In fact, let me just leave this as pass over here, and I'll create an instance of this payment class. So I'll create an object over here. I can say payment1 is equal to payment, and this is where payment1 is an object. It is an instance of the class. So it takes in the blueprint defined by the payment class, and it's an instance of that. So this is an object over here. Payment1 is an object. It is an instance of the payment class. So all of the blueprint defined in the payment class, the attributes, the functionality, the data, all of that defined in the payment class, all of that comes into play in payment1, which is an object, which is an instance of the payment class. Now over here, how do you accept parameters? Like for instance, let's say I want to pass in the parameter recipient, the amount, and let's stick to 2 parameters for now. How do you accept these 2 parameters in the payment class? So we use the init method for that, and this takes in by default a parameter called self. Now self is the same as payment1. So as you might know that you can have different instances of the same class. I can have payment1 for maybe one transaction. I can have payment2 for another transaction. So let's say another transaction will be called payment2, and this 2 will have a recipient, this 2 will have an amount. So payment2 is also an object of the payment class. Now, how do you keep track of each object over here? We use the self keyword for that. So self refers to the instance itself. Now I can add to that instance. I can say, okay, now self.recipient equals whatever input parameter given over here. So here we have given a recipient over here. Let's say the recipient is I don't know, person A, and amount, let's say it's 25 units, and over here the recipient is person B, and the amount is 50 units. So self.recipient is equal to recipient. And what I'm doing by this is that I'm saying that the payment1 object, you add to that payment1 object, which is self, you add to that payment1 object, you add a property called recipient, and make that equal to the recipient input, which is given over here. And to understand what that means, I'm going to print payment1 dot recipient. And if I run this over here, okay, so we also need to take in the amount, and I'm going to do self.amount equals amount. So over here we can see that the recipient is person A. So payment1.recipient defines the recipient for this instance. I can do payment2.recipient, and this will print out B, as you can see over here. So just to summarize, a class defines a blueprint, a set of methods, a set of data that can be that pertains to one entity. Objects are instances of a class. You can have multiple instances of one class, and you can accept parameters, input parameters from each object by using the init method, which is by default called when you create an object over here. When I'm creating payment, this init method is called. So you can use the init method to accept input parameters like recipient and amount, and we say, okay, now add to the current object a property called recipient and make that equal to whatever value is inputted over here. This is one input, this is another input. Whatever input parameter is provided, add that to the self.recipient, which is itself, add that to that instance itself. So now when we define other functions, like maybe let's say check balance, by default I have access to self. By default I have access to the instance itself. So now I can say, okay, now self is the instance itself, and in the init method we added properties like recipient and amount to the instance itself. So now in the check balance method I have access to those parameters, I have access to those variables. So I can print self dot amount. Okay, let's say we have an initial amount, and after the transaction I'm going to return self dot initial minus the amount of transaction. So over here let's print payment one dot check balance, and this is initial, not self dot initial. So initial minus self dot amount, and let's say initially he had 500 units of cash, and now if I save and run again, you see we have 475 left. So we've called the check balance method, we provided an initial amount, and we subtracted the self dot amount, which we remember we added in the init method. So hopefully that makes sense. If this is the first time you're learning object-oriented programming, this may sound a bit complicated, but if you still don't understand it, I encourage you to revisit this section again, and hopefully you get in the second time. So after you have understood what instance variables are, effectively variables that pertain to one instance, like the recipient, the amount, we'll move on to class variables. And class variables generally are for the entire class, for all of the instances. These are stuff like constants. Maybe you have a constant like the dollar to pound ratio, that's one constant, and that will be same for all payments, that will be same for all payment instances. So those are class variables that are generally same for all of the instances. So let's learn about class variables in the next section. So in the previous section we talked about instance variables and how we can create variables pertaining to each instance of the original class. So over here we set the recipient and we set the amount of the transaction for each payment, and in that way we created instance variables because they were pertaining to each object. They were not the same for all of the instances. Like for instance, if you make one transaction, you will have a different amount compared to if you made another transaction. So that's why we created instance variables that were unique to each transaction, to each object. But on certain occasions you need to have class variables wherein you have the constant value for all of the instances, and that's the main purpose of introducing class variables. Now in this example, let's assume that this class payment acts like a ledger for an individual who's making payments on the internet. So let's say he's making a bunch of payments on the internet, and whenever he makes a new payment, an object is created. So payment 1 corresponds to one transaction, payment 2 corresponds to another transaction. So whenever he does a new transaction, a new object is created, and this check balance method is run to check how much balance is remaining after each transaction. In this situation, we don't need to call the initial amount for every single object, because the initial amount would be the same for no matter how many transactions he does. The initial amount that he started with would be same. So in this scenario, we need to use a class variable to represent this value of initial. Initial being the amount of money he had before doing any transactions. So to do that, I can create a variable over here. Let's say initial balance, and let's set that to 1000. And now how do we access this class variable inside this check balance method? So first of all, we don't need to accept a variable, a parameter over here, so we can remove that. And instead of writing initial underscore balance, because even if we do initial underscore balance, you'll see that we're getting this green highlighted, this yellow highlighted problem over here, saying that initial balance is not defined, even though we've defined it over here. And that's because to access a class variable, we need to write the name of the class before the name of the variable. So over here, I can say payment dot initial balance. And in this way, if I remove the second payment and just run this command, you see we get that the remaining balance is 975 units. So that's the basic gist of class variables, and with that knowledge, let's move on to the next section. In this section of the course, we will be talking about class methods and static methods. So traditionally in these classes, you saw that each method accepted the instance itself. Like in this situation here, when we created payment 1, which represents a transaction. So in fact, I'll just call it transaction 1. So, and let's update that as well. I'll remove that for now. Okay. So in this example, we created an object called transaction1, which represents a transaction, and it is an instance of the payment class. So it's an object which is an instance of the payment class, and each method in this class accepted the instance itself, the transaction1 itself. It's as if the first parameter of each of these methods is the instance itself. And we do that because in the init method, we can assign a bunch of properties to that instance, given these input parameters over here, like recipient and amount, and then we can access those parameters pertaining to one instance in the other methods as well. But sometimes you don't want the self to be returned. You don't want to have access to the instance, which is transaction1, but rather you want access to the class itself. Like say, for instance, we want to update this initial balance. Now, one good way we can do that is we can create a class method which will take in the class as an input, and then we can update the class variable over here. So for that, we can use a class method, and how you create that is you use a Python decorator. Now, we don't really need to know much about Python decorators, except that they modify the functionality of our class method. So I'll use the class method decorator, and now whatever method I define over here, which will be update initial balance, this method will be modified so that instead of accepting self, it accepts the class itself. And we don't use the parameter name as class, but rather CLS, because that is already reserved for creating a new class. So update initial balance, and let's take an input as the new balance, let's say. Over here, what I can do is I can say class dot initial balance, and that's the same as doing something like this over here. After the class in line 16, updating the initial balance to new balance is the same as doing the following. Payment dot initial balance equals, I don't know, if the new balance is 50, like so. So it's effectively the same thing, but we're now creating a class method and including that functionality inside the class itself. So now if I do transaction1, or let's do payment dot update initial balance, and I set the new balance to, let's say, 800, and then if I print transaction1 dot initial balance, and in fact we can even print it, yeah, this works fine. So if I run this now, you see we get 800. So since we modified the payment class's initial balance, all of the instances initial balance also gets modified, and that's why transaction1's initial balance is still 800. If we create another transaction, it will also have 800 because it's an instance of the original class. And since we've changed the class variable itself, even the instance variables feel the same change. So I can even do print payment dot initial balance, and we'll get the same response. If I run this, you see we get 800 again. So that's a class method. Now sometimes you need to use static methods, and static methods are basically methods that do not accept any input parameter by default. So in a traditional method in a class, we by default accepted the instance. In a class method, we by default accept the class. But in a static method, we by default accept nothing. So that's effectively a simple function, but we want a function inside a class because it is closely related to the class. So maybe one type of static method we can add is checking if the transaction can be held, because checking if the transaction is between the working hours. So maybe that's between 8 a.m. to 5 p.m. So if a transaction is not within those bounds, then we'll have to return false, else we can return true. So for that, I'm going to create a static method, and the exact same way we do at static method, and then over here we can say check valid transaction, and this will take in nothing by default, but I want to take in two parameters, the hour and let's say the 24-hour system. So I'm going to say if hour is greater than equal to 8 and hour is less than equal to 5 p.m., which is 17, I'm going to say return true, else let's return false. So, and this works because if the condition is true, we'll return true and exit this function, and we won't reach this ever. But if this condition is not true, then we won't exit the function and we'll directly return false. So now let's try this. So I'm going to say, let's get rid of this as well. And I'm going to do transaction1 dot check valid transaction, and we're going to say the hour is 13, and let's print this. If we run the file, you see we get true. If I give in something like 24, or let's do 23, 24 is invalid, we get false. So that's the basic idea of class methods and static methods. And with that knowledge, I'm going to go to the final section of object-oriented programming, which will talk about how we can inherit from parent classes and all of that. So for all of that and more, I'll see you in the next section. So now it's time to talk about inheritance and how we can inherit the properties and methods from another class. And to do this, I'm going to use an example of a website. So in a website, you have multiple pages. You have the home page, you have the about page, you have the contact page, and I'm going to create a base class, which is like the fundamental class, and that's going to be the page class. So this class is going to be page, and this is going to have its own init method. So the page class will take in properties, parameters, like first of all, it'll take in self by default, and then it will go ahead and take the heading of the page and the body of the page. So over here, I'm going to say self.heading equals heading, and self.body equals body. Moving on, I'm going to create a method called create page. So over here, I'm going to do create underscore page, and this will just return HTML code of that page. So keeping it very simple, let's just have a header tag. And if you're not sure, if you haven't learned HTML code, all this is doing is creating a heading using a header tag, and it's creating the main body text using a paragraph tag. So over here, I'm going to say h1. So this is the heading tag, and within it goes the heading. So I'm going to use an f string to embed self.heading here. So whatever the heading is, we're going to embed it inside the heading tag, and then we're going to create a new paragraph, and this will contain the body. So this opens the heading tag, this closes the heading tag, and within the heading tag you have the value of the heading, which, remember, we assigned to the instance of the page by accepting the heading as a parameter in the init method. And over here as well, same thing, we're going to do it with self.body. Over here, I'm going to return the HTML code, and that's going to be pretty much it for the page class. Now I want to create another class for the contact page, but there'll be a lot of overlappings. The page class is like a bigger circle, and the contact class is a smaller circle within it. So the page class is like the parent class of it, where the contact class has to inherit stuff like the heading and body from the page class itself. Because if, okay, let's just assume we were creating a contact class like this in a simple way, then we'd have to copy all of this code and paste it again. like so, and this is a very inefficient way of working because we have the page class, which is the base class. Why don't we just inherit the init method? Why don't we just inherit the create page? Because they're effectively the same methods, because they have the same functionality. Contact page is after all a page, and therefore it will inherit some of the methods and some of the properties like self.heading and self.body, and some of the methods like create page from the page class. So how do you inherit? How do you inherit these properties and methods from the page class? Now in Python, you use the following notation. So you go pair of parentheses and you write the name of the class you want to inherit from. And with that, all of this code is saved. I don't need to rewrite it again. And all I need to do is pass, essentially do nothing in the contact class. And now let's create a contact page. So I'm going to say contact underscore page is equal to contact. And I'll provide a heading. Let's say contact us. And the body text will be, please give us your feedback. Now I'm going to say contact page dot heading. So let's see what the heading is. And if I run this, okay, so I need to print that. So let's print it. And if I run, you see we get the heading is contact us. So even if we don't have an init method over here, it doesn't matter. The Python would first look in the contact class to see if there is an init method. It doesn't find it, it'll go to its parent class, which is the page class. And over here, it finds an init method, and it assigns self.heading to heading. It sees that over there. And from that, you see that the contact page instance gets the heading variable attached to it. And then when we print it, we get contact us as the heading. So it first looks in the contact class. If it doesn't find an init method, it will go ahead into the base class. So another thing we can do is create a page. We inherited that method. So if I run now, you see without any code in the contact class, it doesn't matter, we're getting the same output here because we've inherited the method and the variable from the page class. So now with that done, I want to talk about one more thing, which is the isInstance function. The isInstance function in Python is used to check if an object is an instance of a particular class. I'm sorry for that. So let me repeat that again. The isInstance function checks if an object is an instance of a particular class. Like for instance over here, let's print isInstance contact page of the contact class, and as you would expect, it says true. Yes, the contact page is an instance of the contact class because we have written contact over here, it's an instance. But another thing we can check for is if it's an instance of the page class. And if I run this now, you'll see that too will return true, because although it's not directly linked to the page class, the contact class inherits from the page class, and therefore contact page is also an instance of the page class. We'll use this function isInstance a lot during the coding of our of our programming language. So it's important to note the functionality of isInstance. Another thing I want to talk about is the super function. So over here, I'm going to create the init method. And let's say I want to accept another parameter for the contact page. Let's say I want to accept the email address of the person who wants to contact me. Now that's not there in the base page class because not every page would need to extract the email address. But it turns out that the contact page does need to do so. So over here, it'll extract the heading, first of all self, then heading, then body, then the email address. And over here, what do? Do I just copy this part over here and then do self.email ID? Is this the correct way to do it? But let's try it out. So if I give an email, let's say if I give that email in and let's print the email ID, If I run this, you see this will work. We get the email ID, but code repetition is not always appreciated. It's never appreciated, in fact, in programming, and therefore, to avoid this repetition of assigning heading and body to the instance, instead of repeating this, since we already have that functionality in the page class, we use the super function. So the super function calls the init method in the parent class, which is page. It calls the init method, and we can pass in parameters heading and body. So this ensures that the init method is called in the super class, and the super class is the page class. So this is like saying go to the page class and then run the init method and provide the heading and body as parameters. So that's effectively what the super function is doing. So after we have handled heading and body, then we do self.emailid equals email ID, and let's create another function over here. Let's say I want to create a contact button, and this will take in self, and all I'm going to do is return button, and then inside the button I'm going to say self.emailid contact now, something like that. So if my name is, if the email ID is abc@email.com, then it'll say abc@email.com contact now, and this will be inside a button. So in HTML, the button tag is used to create a button. So over here, let's do the same thing. Let's contact page. Now we're going to create the contact button, and let's print. And hopefully this works. There we go. Button abc@email.com contact now. So this is the power of inheritance. We are adding, we are extending the functionality of the base class, which is the page class. We're extending its functionality by adding our own methods, while also inheriting the most fundamental functionalities like create page. And we're also inheriting the init method over here. Previously, we didn't even have to write the init method. It automatically found it from the page class and executed that. So that's the power of inheritance. And with that, I'm pretty much done with object-oriented programming. Of course, if you want to understand object-oriented programming on a deeper level, there are several other concepts to understand. But I think that we've reached a fair stage now where with this base knowledge, we can move on to the next section. So in the next few sections, we'll be talking about data structures, and we're going to start off with lists. Now, lists are like regular lists that we talk about in common language and everyday language. You can have a list of grocery items. You can add to the list of grocery items. You can remove something from the list of grocery items. You can add something at a certain position. So it maintains a sequential order as well. That means it respects sequence. That means you can add elements at a certain position. It's not just that you can add them at the last position or at the first position. So let's demonstrate everything about lists in Python. So this is the simplest form of data structure. We'll go on to more complicated forms. Like eventually we'll talk about binary trees. So anyways, let's start with the list. How do you create a list in Python? You first create the name of a variable. So I'm going to call the variable R, short for array. So, or let's just call it, I can't use list because that's a reserved keyword. So let's just use A. Let's call the list A. And you create a list by using these square brackets. And I can create the first list by saying 1, 2, 3, 4. And that's one list over there. You can add to the list using the append method. So all of this list in Python are built-in classes. So that means if I print is instance A of the class list, and that's a built-in class. If I run this, you see it will return true because it's a built-in class. And when you use these square brackets, you sort of create an instance of the list class. So over here in that list class, there is a method called append. So I can append, let's say a number, let's say append 5. And now if I print A, you see that the output will be 1, 2, 3, 4, 5. The append method adds the last element. There is another method too, which is called insert. And the insert does not necessarily add at the end of the list. It can add things even in the middle or whichever position you define it to be. In Python, the position are defined by starting with the number 0. So this first element is given the index 0. The second element is given the index 1 and so on. So 0, 1, 2, 3. So that's the order. So you start off with 0. So if I say print A square bracket 0, that means I want to access the 0th element, which is the number 1. So we'll get the number 1 over here. So we can insert, as I said, so I can insert a certain data. It can be anything. It can be a number, it can be text, whatever. So I'm going to insert the number 8 at position 2. So that means 0, 1, 2. That means it should be after the number 3. So let's print A now and see what we get. You see, it's okay, I reversed the order, my bad. So we have to mention the position first and then the number. So 2, 8. Now let's see if it works. So if I run this, you see we get it before 3. So 1, 2, 8 and 3. So at position 2, so 0, 1, 2. So now this is a position 2 over here. And following that, there's the number 3, then 4 and 5. So that's the insert method for lists. I can even add a text here. So we create text using these double quotes. And let's say text. And if I run this, we'll get 1, 2 text at the second position. Remember 0, 1, 2, second position, 3, 4, 5, and that's how it works. You can reverse the order, so you can have 5 first and 4 second and so on by using the reverse method. So I'm going to say a.reverse. And if I run this, you see we get it in reverse order. We can sort it in ascending order, and we can, for now I'm going to say ascending order of numbers. So let's say I have the number 9 here, and I'm going to print A over here before the sort. So before sort, and then I'm going to sort a.sort, and then I'm going to print A again. And if I run this, you see I'll get before sort it's 5, 4, 3, 9, 2, 1, but after the sorting process it's stored in ascending order. Another method is the pop method, and this returns the last element of the list and also removes it from the list. So if I right now, let's remove all of this clutter, and if I do a.pop and then I print A, let's run this again, and you see we get 1, 2, 3. And in fact, I say if I can say last underscore element is equal to a.pop, and if I print the last element, I'll also get what the last element was. So if I run this, you see I get 4 was the last element, and now what remains of the list A is 1, 2, 3. So you can also remove all of the elements by using the clear method. So over here I can do a.clear, and if I print A, run it, you see we get an empty list which is symbolized like so. So now let's move on to a few more operations. One operation you have is, let's say I have the list 1 like that. Now I can print, or I can do A equals A times 5. And now let's print A. You may think that makes no sense, but that essentially just multiplies this item by 5. So that means this item will be present 5 times now. So 5 times 1 is 5. If this was existing twice, then it will add the same array 5 times to itself, and A would look something like this. So if I run this, you see we get the array with 10 ones, because the first base array is with 2 ones, and then you multiply that with 5 and you get 10 ones. So that's how you can multiply arrays. You can even add arrays to each other. So if one array is 1, 2, another array is 3, 4. Now if I print A plus B and run this, you see we get 1, 2, 3, 4. So that's how we can add or multiply arrays. One more thing you can do is you can iterate over a range of values in an array. So like say for instance I have 1, 2, 3, 4, 5 and 6. Now if I print a 1 to 3, so a 1 to 3, let's see what we get over here. So if I run this, you see I get 2, 3, and this starts off from the index 1, which is here, moves on to index 2, and it excludes the last value here. So if you want to include the last value, you'll have to add by 1. So 3 plus 1 is 4, and in that way it will include 2, 3, 4 like that. So let me just rephrase again. So you have at index 1 you have the number 2, so 2, 3, 4, and this is index 3, 0, 1, 2, 3, and this last, since it's 4 over here, but when you're taking it over a range, it does not include the last number, it does it 1 minus that. So a 1 to the 4 returns the list from a to the power 1 to a to the power a3. So index 1 to index 3, that's how it works. You can also have no number at the start, and that will return everything until the index number 3. So if I run this, you see everything until index 3 if you don't specify a number over here. If I specify a number over here, it will be from index 1 to index 3, but if I don't specify it, it will be from the start to the index 3. Now after that you also have copying arrays. So how do you copy copying lists? So how do you copy one list to another list? So let's say I have this list over here, a equals 1, 2, 3, 4, 5, 6. Now a2, I want to copy list 1, so I'm going to say a, and let's see what happens if we do this. So now if I print a2, you see we do get 1, 2, 3, 4, 5 and 6. But check this out. If I do a2 dot append 7, and now I print a2, obviously it will have the 7th number after it. But if I print a and run this again, you see even a has experienced that change. So when you equate these two together, even a experiences the operations you do after that, after line 2. If you don't want that to happen, you want to leave a as it is and work with this as a new array, you can use the copy method, so dot copy. And if you do that, you see this change does not get implemented on array A, it's only implemented on array A2. So that's about it for lists. Tuples are quite similar to lists in that they also store data in an ordered manner. So you can create a tuple instead of using square brackets, you use the normal brackets. So over here I can say tuple1 equals, and you use a pair of brackets over here, and I can have 1, 2, 3. I can print the first element of the tuple, which is the 0th index. I can, let's just do that for now. And you see we get 1 over here. So that's how tuples work. It's very similar to lists, but they have a few distinctions that you need to keep in mind. One of the distinction is that a tuple is immutable. So if I try to do the following, tuple 1, 0, and I try to change the 0th index, so let's say the number 5, and I save it, you see we get an error. Tuple object does not support assignment. So this is why tuples are immutable, they can't be changed, whereas lists are mutable. So if I do list1 equals 1, 2, 3, and then I do list1 0 is equal to 5, and let's comment this one out, and I run this, you see we don't get any error over here. And let's just print list1 as well. If I run this, you see we get 5, 2, 3, because lists are mutable but tuples are not. One additional thing you need to note about tuples is that if you have a tuple with one element, then you can create them by using the following notation. You can't have no comma over here, because if you do brackets, 1 brackets, that will mean that this is just a number inside a pair of brackets. It does not resemble anything. But if you put a comma over here, you would realize that that's a tuple. So in fact, let's try and see the instances, whether it's an instance of tuple or not. So let's print is instance tuple1 of tuple. If I run that, you see we get false. But the second I put a comma over here, I'm telling Python that this is a tuple. I want to create this as a tuple. So if I run this, you see we get true over here. Now it's also possible to convert tuples to lists and lists to tuples. So I'll delete all of this now. And I can say list1 equals tuple or equals list of tuple1. And if I print list1, you see it will be a list, as you can see. And if I do list1 over here, and let's create a list over here, and I'll do tuple1 here, and let's create a tuple from the list. You'll see that that too will work. We get a tuple over here. So that's about it for tuples. Let's move on to the final sort of simple data structure, which most of you might already be familiar with, but I thought it would be a good idea to give you a refresher about these data structures. So the last one we'll be talking about is dictionaries, and then we'll move on to a few advanced data structures like stacks or binary trees, which we will be using in this course. So I'll see you over there. So how do you create a dictionary in Python? Well, there are two ways to do it. So the first way is a simple one. You just use a pair of curly braces, and then the first thing you mention in a dictionary is the key. So in a dictionary you have key and value, so you have key value pairs, and an example of this will be the following. So let's say I have an employee and his name is John. So over here, name is the key, John is the value. This employee will have an age, and you have to also include that in double quotes, and his age is 19. This employee will have a profession. Let's say it's accounting. So that's how dictionaries work. You have a key, you have a value, and these pairs you can have n number of them in a dictionary, stored in a dictionary. So the purpose of dictionaries is that they can store two values, key, they can store two pieces of data, key and value, and they're actually pretty useful when, for instance, creating a Lexer, where each token will have a data type and a value. Like for instance, the number 5 has a type of integer and has the value of 5. So in that sense, dictionaries are really useful because they allow us to store two pieces of data. How do you access values? So you can say dict1, say the name of the key. So let's say the name, and let's print this. So similar to an array, how we use the square brackets to access a certain index, we'll use a square bracket to access the value of a certain key. So let's print this, run it. We get John. We can do age, and we'll get 19. And this doesn't necessarily have to be a string. It can also be a number. So for instance, let's say 5 is, I don't know, 26. Okay, this makes no sense, but I'm just trying to show how you can also store the key as an integer, as a number. So over here, I can access the key 5, and that will return 26. One more thing you can do in dictionaries is traverse through them, iterate through each item of a dictionary, and you use a for loop for that. So I can run a for loop. We can extract the key and the value in dict1 by using the items method. The items method is a certain method present in the dictionary class, which is inbuilt in Python, just like the list class and the tuple class. So over here, we're extracting the key and the value, and I can print that in an S string. I can print key with a space bar and then value. And if I run that, you see we get name John, age 19, profession accounting in a new line every single time. So that's the basics of dictionaries, and that's all you need to know for this course. And with that knowledge, let's now move on to a few more complicated concepts in data structures. In this section of the course, I've brought an interesting activity that you can do using the existing knowledge that we've built so far. So we are going to create our own class for a data structure known as a stack. Now, a stack is effectively just, it's just like that. It's just what the word describes, a stack. You can have items stacked on top of each other. You can add an item at the top of the stack, but you cannot add it in between the stack like we did in a list where we added items in a certain position of the list. Well, we can't do that with stacks. The only three operations you have is you can add an item on top of the stack, you can remove an item from the top of the stack, or you can read the value of the item at the top of the stack. So I have an activity for you. How about try creating a class that performs all of these functionalities? So we'll have a class called stack, and it will have an init method, of course, but I won't write that for now. It will have three functionalities: push, which means adding to the stack, adding an element to the end of a stack, to the top of the stack. We have pop, adding an item to the top of this, removing the topmost item from the stack. And you also have peek, which is reading the value of the item on the topmost of the stack. So these three functionalities, push, pop, and peek, can you try executing them using Python lists? So you will be using Python lists as a data structure to create the stack. So now let's move on to the task. How does this work? So I'm going to first create the init method, which takes in self, and it will, yeah, that's it, self. And over here, I'm going to create the stack. Now the push method adds an item to the top of the stack. So this will simply append to the list whatever item. So we need to take self over here first of all, and we also need to take the item that you want to push to the top of the stack. So I'm going to say item over here. We're going to append item. We can pop, as in remove the item at the topmost of the stack. And for that, we can use the pop method in list. So you can do pop, and I'll also accept self here. And we can return self.stack.pop. This removes the topmost item from the stack. Peek will just return the topmost item from the stack. Now in Python, to extract the last item of a list, because since we're using list to represent the stack, the topmost item is the last element of the list. So how do you extract the last element of the list? For that, I'm going to use self first of all, and I'm going to say last underscore element is equal to self.stack, the length of the stack, -1, because the indexing starts from 0. And in this way, we're extracting the last item of the list, which corresponds to the topmost element of the stack. So this is the last element, and I'm going to return that last element. So now let's try working with the stack. So I'm going to say stack1 is equal to stack, and I'm going to do stack1.push. Let's push the number 5, stack1.push number 3, stack1.push the number 7. And now I want to peek. I want to see the topmost element of the stack. So I'm going to print stack1.peek, which will peek at the topmost element of the stack. Since the bottommost is 5, then in the middle there's the number 3, and then the top of the stack is 7, we should get the number 7. So if I run this, I get 7 over here. So that's it from this section. I feel that this was a good exercise to get us warmed up for our upcoming challenges in creating the programming language. So with that exercise, let's move on to the next section where we will be talking about binary trees. A binary tree is a form of hierarchical data structure. It looks something like this. So you have the following placeholders. You have A, you have B, C, all of these points. And these points represent a storage of data. They're called nodes. Nodes are a unit of data. It's a representation of data. It's a placeholder for a piece of data. So B over here, C, and then we can do D, E, like so. And this is a binary tree. Now a binary tree means that each node has a maximum of 2 children. The child of node A is B and C, so this is the left child. This is the right child. So the children of node A are the left child and the right child, which is node B and node C. And in a binary tree, every node has a maximum of 2 children. As you can see, nodes D and E have no children, and they are called leaf nodes. Node B has 2 children. Node C, maybe we can have 1 child to it, like that. So the idea is simple. Binary trees have a maximum of 2 children. Every node in a binary tree has a maximum of 2 children. A bit of more terminology is the fact that every single level is given a number. So this is called level 1, and it includes only node A. This entire thing is called level 2, and this entire row is called level 3. So that's just the terminology used in describing binary trees. But what's the use case of it? How does it work? We'll look into that in the next section. The most important part of binary trees is the way in which we traverse to them, the way in which we visit each node and analyze and process each node. So there are 3 ways of traversing a binary tree. And just before we get into that, I'm going to talk about something called a subtree. So I have the root node over here. This is called the root node, which is at the top of the tree. And it has a few children, 2 children, maximum of 2 children. And every single node after that also has a maximum of 2 children until we get to the leaf nodes, which have no children. So D, and let's do E over here. So in a binary, and I'm going to do one more F over here. In a binary tree, we also have subtrees. So this entire region, which is enclosed by the dotted line, is a subtree. It's a tree within a tree. And now that we understand what subtrees are, we can try and understand the traversal methods, how you visit each node of a tree. Traversal refers to the fact that you have to visit each and every node in a binary tree. So how do you do that? There are various ways in which you can traverse through a binary tree, and we're going to talk about 3 ways. The first is called preorder traversal. Preorder traversal refers to the fact that you first go to the root, you first visit the root node, then you visit the left subtree, and then you visit the right subtree. So I'm going to call the subtree over here subtree 1, and this subtree will be 2. So how can we traverse through this entire tree by using the preorder traversal method? So the first step is going through the root. So we start off with node A, then we go to the left subtree, so then we traverse through left subtree, and then we traverse through the right subtree. Now we need to understand how we traverse through the left subtree, which is subtree 1, and we use the same pattern over here. We start off with the root, so we go from B, then we go to the left subtree, and the left subtree is just node D, so this is the left subtree over here, so that's node D. Then we go to the right subtree, which is node F. So that's what the preorder traversal of subtree 1 looks like. The preorder traversal of subtree 2 will look like, first we start off with the root node. There is no left subtree, so we don't do anything. Then we move to the right subtree, which is E over here. So in preorder traversal, the order of traversal is A, B, D, F, C, E. And this is known as preorder traversal. We sometimes use preorder traversal. We visit the tree in such a way to accomplish certain tasks. in our scenario where we want to parse inputs in a certain programming language and then then execute it, we'll be using post-order traversal. So let's take the example of an expression 1 plus 2 times 3. Now, how does all of this relate to a binary tree? So we can represent 1 plus 2 plus times 3 instead of this expressed in a linear way, like a list of tokens, which is what we do after step 1, after lexical analysis. Step 2 involves making this linear data structure and converting it into a hierarchical binary tree. So how can we express this expression as a binary tree? So we start off with the plus operation, which is the topmost, which is the root node. Then we go left, which is the number 1. Then we multiply 2 and 3. So this is the binary tree of the expression 1 plus 2 times 3. And the way in which we traverse it affects how we evaluate the expression. So in post-order traversal, so we talked about pre-order traversal in the previous section. Now I'm going to talk about post-order traversal. In post-order, you start off with the left subtree, then you move to the right subtree, and then you move to the root node. So the left subtree is the following dotted line. The right subtree is also the following. Left subtree, it's just, so I'm going to call this subtree A. I'm going to call this subtree B. So subtree A is equal to just 1. That's the only thing that's the only way in which you can traverse subtree A. Subtree B, if you want to do a post-order traversal on this, you start off with the left subtree, which is the left node over here, the node 2. Then you move to the right subtree, which is node 3. And then you do the root node, which is multiplication. So now, finally, to evaluate the binary tree, we start off with the left subtree, which is A to B to the root. And that's 1, 2, 3, multiplication, root. So that's the way in which we traverse through this tree. It's called post-order traversal. And the idea in post-order traversal and how it relates to computing our expression is the fact that the order of operations with higher precedence lie lower down the tree. And in expressions, when evaluating expressions, we give preference from left to right. So if you compute 7 divided by 2 divided by 3, we compute this first, and then the answer of that we divide it by 3. So the higher precedence is given to left than the right. So this is one fact, and the other fact is that we give precedence to multiplication and division more than the preference to addition or subtraction. So in this scenario, the order of operations with higher preference are lower down the tree. They have a higher level. So remember, this was level 1, so they'll be lower down the tree, they'll have a higher level. And by traversing them in a post-order manner, like 1, 2, 3, multiplication, and then the root node, by traversing them in such a way, we are first computing 1, then we are computing the multiplication, and then we are adding those two together. That's what the effect of post-order is. So now let's understand how post-order traversal relates to computing an expression. So let's say we have the following expression, 1 plus 2 times 7. So over here, we're going to have addition first. Or in fact, I'm going to do multiplication first because we already used a similar expression. Let's do 1 times 8 plus 7. So plus and then multiplication, 1 and 8 and 7. So in this example over here, let's try to do post-order traversal. So remember, it's left subtree, then it's the right subtree, and then it's the root node. So the left subtree is the following. And in here, again, we have to do post-order traversal. So the left subtree of this subtree is the number 1. then you go to the number 8, then you go to the root node, which is multiplication, and then again we move to the right subtree, which is 7 over here. This is the right subtree, and then we move to the operation plus. So that's the post-order traversal of how this works. And now let's try and see how we can compute an expression using post-order traversal. So I'm going to erase this bit. And over here, so over here, let's see, by following this order of operation, by following this order of traversal, how we can compute the expression. So remember, the first thing we're going to do is visit the root node, the node 1, which is over here. The first thing we do is visit this, so we visit this A. Then the second thing we do is visit this, so B. Third thing we do is visit this, so C. Then D, and then finally we visit the plus operation, so E. So we start off with first, then 8, then multiplication, then 7, and then plus. So how does this relate to computing an expression? So we first visit this node over here. So I'm going to call that node A. We first visit node A, and we process it. So that's the number 1. So we first process that. So let me keep that over here. So 1, we first process that. Then we go to root B and we process that. We get the number 8. So now we've processed that as well, and it's the number 8. Then we go to root C and we process that. Okay, now we see it's the multiplication of 1 and 8. So then over here, all we do is 1 times 8, which is equal to 8. So in multiplication, so there are 2 types of visiting. One, you visit a number in which you just return that number 1 or 8. The second type of visiting is when you visit a binary operation. Over here, plus is a binary operation, it's adding 2 numbers. Multiplication is a binary operation, it's multiplying the left child node and the right child node. So when we visit a binary operation, we have to multiply the left child node and the right child node. So now we visited the multiplication node, which was node C, and we computed it. It turns out to be 8 times 1, which is 8. So we visit 1 first, we visit 8, then we visit multiplication. So we're done with this, and this. Then we visit node D and we compute it. It turns out to be value of 7. I'm sorry, I just had a glitch over here. So after we've processed node 7, the following node over here, after we've processed that, then we go to the root node, which is over here, and we do a binary operation. We check the left node, we check the right node, and we compute them, we add them together, and the output turns out to be 15. So that's how we will be interpreting our input expression, and this can be replicated for all of the input expressions in the programming language. Like say for instance, we have an input A equals 7. So then the operation would be equals and then A and then 7. Then we'll have to traverse in the post order method and we'll have the similar output. So that's how we're going to compute expressions. That's how we're going to interpret our parse tree, by following a post order traversal method. And with that knowledge, and I hope that you understand how we are going to compute expressions, because this is an integral part of our course. So now that you've understood it, let's move on to the next section, where we will be constructing a binary tree and doing some exercises with them. So in this section of the course, we'll be creating a binary tree, essentially representing them in a programming language. As of now, we've just been drawing them and talking about them in a theoretical way, but now we'll be creating a binary tree in the Python programming language. So the first thing we need to do is create a class for the binary tree. In fact, I'll just call it tree for now. And this will have the init method, and it will take in a root node to start off with. And the root node, I'm going to assign it the value of, let's say, 5. But I don't want to work with just numbers for now, because I know that nodes, the nodes can also represent other pieces of data. So to represent a node, I'm going to create its own class. So I'm going to create a class for the node as well, the node class. The node class will accept one parameter. It will be the value of the node, and I'm going to say self.value is equal to value. And the node has two parts. As you remember, in a binary tree, a node can have a maximum of 2 children. So I'm going to represent the left child by initially none. So initially the node has no children, and the right child will also be equal to none. Now let's go back to the tree and let's set the root to be equal to a node with the value of the root. So over here, we can create our first basic tree by saying, okay, the tree is equal to an instance of the class tree, and the root node will have a value of the number 5. So this is just creating the number 5. It has no left node, it has no right node for now. But let's add those parameters in. So I'm going to say tree dot root. So the root variable, now we're accessing that. Since it has a class of node, I have access to these parameters left and right, so I can assign these values. I can say tree.root.left is equal to 3, and tree is equal to node 3. Let's do node 3. And tree.root.right is equal to node 4. What is the effective representation of this? This has 5 at its root, and it has 3 as the left child. The right child of this node is 4. So this is the diagram. This is the tree diagram that we have created using Python code. So there is a tree. It has the root of 5, and that's just a node with left and right assigned to be 3 and 4. And the left and right nodes of 3 and 4 are by default set to none. So that's how we can create a binary tree in Python. Now let's go ahead and do pre-order traversal on this tree. To perform pre-order traversal, I'm going to create a method called preorder in the tree class itself. So I'm going to say def preorder, and this will take in self, and the first parameter it will take is the starting point of the preorder, and this will be the root node. But as you will see, we will change the starting node, and we'll be using some recursion in this algorithm. So so the starting node initially will be the root node, but we'll take that as a parameter. And another thing we're going to take is the records field, and I'll explain what this means in just a second. But for now, I'm going to say if the starting point is not none, which means if the starting point exists, because remember, for the left and right nodes, we set them as none. So all we're checking is if they're not none. That means if the starting point exists, if the node exists itself, then the first thing we're going to do is we're going to append that node to the records list. So the records over here corresponds to a list, which will be an empty list for now. And over here, we're going to append it the start.value. So let me talk about what this means again. So remember, in pre-order traversal, we go in the order of root, then we go to the left subtree, and finally we do the right subtree. So in this case, let's look at the diagram. So it's 5, the tree diagram. So it's 5, starting off with 5. Then we go to 3 in the left node, and then over here 4 in the right node. So we want to start off with the root. So in the pre-order traversal over here, we're going to call pre-order. So I'm going to say tree.preorder, and I'm going to pass in the root first. So I'm going to say tree.root, that is the starting point, and records will be an empty list. So now let's see what happens. So the first parameter is tree.root, second parameter is an empty array. So tree.root is the starting point, and start is not none, and therefore it will append the starting point, which is the root itself, to the records. Records will be tracking our visits, so the order of visits, that will track the order in which we traverse through the nodes. So the first thing that will be appended to the records list will be the root itself, and that conforms, that pertains to our rule of pre-order traversal, where we start off with the root. So indeed, by appending the starting point value, which is the root's value, to the records list, we are abiding by the rule set by pre-order traversal. Now let's go ahead. Now we want to do pre-order traversal upon the left subtree, because remember, when we were computing preorder traversal, we started off with the root, then we went to the left subtree and we did preorder traversal within that left subtree. So now to compute the left subtree, we need to do preorder traversal in the left subtree. So I have to do records equals self.preorder traversal. So we have to do a preorder traversal on the left subtree itself. So the starting point now won't be the root, it will be the left node, left child of the root. So I'm going to say start.left. So over here the starting point is root. I'm going to say start.left. We want to do a preorder traversal on the left subtree itself. So this is where recursion comes in. Recursion is the act of calling your own function inside the function. So we're calling the preorder method inside the preorder method itself. So over here we're doing start.left. So we want to do preorder traversal on the left child, on the left subtree. So how will this look like? So we start off with 5, then we go left and we start off with number 3, and we do preorder traversal on this subtree over here. So right now there's no subtree, but let's say there was. So I'm gonna move them to the right, and over here I'm going to add one final item. It's going to be, let's say, the number 2, and over here we have 2 child nodes for this node 3, and let's say 8. So over here we start off with the root node, append that to the records array, and the first thing we have is the root. Perfect, it's working perfect. So now we move on to the left subtree. We do preorder traversal upon this node 3 over here, and that will call, again, that itself will call start.left. So it will do preorder traversal on this left subtree itself. So we're calling preorder traversal on the left subtrees until we hit a leaf node, where self.left is equal to none, and we break out of this. So that's the power of recursion. So now we're going to do records. So remember, we had to compute root, then left subtree, and now we're going to do right subtree. So records equals preorder start.right, and over here I also need to provide the records list itself as an input. So now let's see how this works. So I'm gonna run preorder traversal, and I'm gonna print the records array. So we're gonna return the records list, and I'm gonna print the output given. And if I run this file, you see we get 534. So okay, I shouldn't have deleted that comment over there. So I'll just copy all of this and bring back that tree. Okay, there we go. So let's paste all of that again. So this is how the tree looks like, 534. So we start off with the root node, then we move left, we compute that left subtree, then we move right, we compute the right subtree. So from root, then left, and then right. Even if we have a more complicated tree, like for instance, we're gonna add, let's say we had that, the left subtree within the node 3. So let's create that over here. We're gonna say tree.root.left, which is node 3. For that node, we're gonna add another left, and that will be node 2. And then tree.root.left.right, its right child will be equal to the node 8. So even if we have this complicated expression, how would the preorder traversal work? We'll start off with the root, then we'll compute the left subtree, and we'll do preorder traversal on that left subtree. So we go from root again, so 5, 3, and then we start off with left subtree, which is 2, and then 8. So we should have the expected output to be 5. Then compute left subtree, so that's, we compute left subtree using preorder traversal. So that left subtree is 3, 2, 8. So this is the left subtree over here. If I can highlight just that part. Okay, I can't do that right now, but let me delete that. So the left subtree is this. So how do we compute that left subtree? Using preorder traversal, we start off with the root, so 3. Then we go to the left subtree of that left subtree, which is 2. Then we move to right. Okay, and here it was, I believe, the number 4. And then we move on to the right subtree, which is the number 4. And this should be the order of preorder traversal. So if I save and run, you see we do get 5, 3, 2, 8, 4. So this is what recursion looks like. Now, if you still don't get it, it's perfectly understandable because this is a complicated concept to grasp initially. So I recommend you to move on to the next section, understand recursion, how recursion works, and we'll be looking at a few algorithms dealing with recursion, and then come back to this section where we will be talking about pre-order traversal again. So in the next section, we'll be doing post-order traversal, and then after that, we'll do recursion. We'll talk about recursion and the types of recursion algorithms. So for all of that and more, I'll see you in the next sections. Now I'll be doing the post-order traversal, which is quite similar to the pre-order traversal, but except remember the fact that we had root over here. That line corresponds to appending to root, appending the root to the records list. This is the left subtree. I feel like I've said that a lot, but yeah, that's what recursion is about, doing things again and again. So left subtree, and this is the right subtree. So this was the order in which we created the pre-order method. And over here, now to do post order, remember that's just left, right, and then the root. So all we have to do is say define post order. In fact, I'll just copy all of this, and starts with self, start, and records. And let's paste. And over here, instead of putting records that append first, instead of registering the root first, I'm going to register the root last. So now let's try post-order traversal of this binary tree. So I'm going to print tree.postorder, tree.root, starting with the tree.root, and an empty array. So if I run this, you see we get we get none because I did not return. So let's return as well. Let's return the records. And now let's run, and you see we get a different order of traversal. Remember the tree order traversal for post order. So how does post order work? You start off with the left subtree, and okay, this seems to be a problem. You should start with 2 and then move on to right and then to the operation. I think I have made a mistake over here. Okay, yeah, so yes, so I forgot to change this to post order because we will be calling the post order instead of pre-order. So I'll do post order here. And if I run this again, you see we get the correct order of operations. We start off with 2, then we move on to 8, then 3, then 4, and then 5. So I'll do this one last time. I'll give this a complete summary of the explanation. If you've understood this completely, congratulations, you can move on to the next section where we will talk about recursion. But I just want to summarize pre-order and post-order one more time. So pre-order, this is how it works. We have created this tree. Then we have the condition, check if the start is none or not. Root is not none. So then we move into this if statement. We append the root because pre-order starts off with the root, then the left subtree, and then the right subtree. So we append the root first to our records array, and the records array symbolizes the order of visits that we've done. So we first append the root, then we go down here and we say records equals self.preorder, and we're essentially doing pre-order traversal on the left subtree itself. So start.left, now we make this the root, and 3 to 8 we make that the left subtree, and we do pre-order traversal on it itself. Then we do pre-order traversal on the right subtree, and then we finally append the records, then we finally return the records. So that's how pre-order traversal works. Post-order, it's the same thing except we do the root at the last. So I hope you get that, and in the next section we'll talk about recursion. So to get you more familiar with recursion, I have prepared 2 problems in programming. One is the Fibonacci sequence, and the other is counting to a certain number. So hopefully these 2 exercises will help you understand recursion, which we will be using a lot in the later stage of this course. So the first problem is the Fibonacci sequence. Now, if you're not aware, the Fibonacci sequence is a sequence of numbers that starts off with the first numbers being 1. And after that, from third number onwards, any nth number, you take any nth number, it's equal to the sum of its previous 2 numbers. So the third number is the value 3. Okay, sorry, the third number is the value 2 because 1 plus 1 is 2. Now the fourth number, what is the fourth number equal to? It's the number 2 plus the number 1, which is 3. The fifth number is the number 3 plus the number 2, which is 5. So that's how you construct a Fibonacci sequence. Now, how do we come up with a program that will tell you the value at a certain position? That given a certain input, like for instance, the number 4, it will spit out the value, the number 3. So how can we come up with such a program? Given an input of the position of the Fibonacci sequence, it outputs the value of that Fibonacci sequence. So how can we come up with such a program? So first of all, I'm going to use a function. I'm going to create a function called Fibonacci, and it will take in the position, and it will return the value at that position. So we're going to use recursion to solve this problem. Now let's take any position, like this is the 4th position. At the 4th position, you're summing the 2nd position and the 3rd position values. So we can define Fibonacci, we can say Fibonacci, or let's say output is equal to the Fibonacci of the previous position, position -1, plus the Fibonacci of position -2. So we have an output. We are recursively calling, again, this is recursion because we're calling a function inside a function. We're saying, okay, the output is equal to the Fibonacci value at position -1 plus the Fibonacci value at position -2. So at position 4, it's the one previous to that, which is the number 2, and 2 times previous to that, which is the number 1. So 1 plus 2 equals 3. Now, this works for most cases, but except for the first 2 scenarios, where the first 2 scenarios, the output is just equal to 1. So to handle this case, I'm going to say, okay, if the position is greater than 2, or let's say greater than or equal to 3, from here, if it's greater than or equal to 3, then we're going to use this expression. Else, if it's not greater than or equal to 3, then I'm just going to return the number 1, because in that case, it's either 1 or 2, and for both instances, the output is 1. So we're using recursion to to solve the Fibonacci problem. We can return the output given a certain input. So now, a better way to write this is I'm going to say output equals 1. Output equals the following if it's greater than or equal to 3. Output equals 1 if that's not the case. And then at the end, I'm just going to return the output. So let's test this out. I'm going to say this response is equal to Fibonacci. And let's say for the first number, and that's pretty simple. That should hopefully respond with the number 1, and I'm going to print the response. So if I run this, you see we do get 1. Pretty simple. Even if we do 2, we should get the same answer, 1. Now if I do 3, we should get the number 2. So let's see if that works. I run, you see we get the number 2. If I try the number 4, we should get 3, and indeed we do get 3. And if I try 5, we should get 5, as you can see over here. Let's try one more. Sixth number would be 5 plus 3, which is 8. So if I do 6 here, we'll get 8. So that's how recursion works. And to be honest, this is not a very efficient algorithm, because we'll have to eventually, as the input number increases to maybe 40 or 50, this thing will take a lot of time to process. So 45, if I input 45 over here, you see it'll take like a few seconds to process. We're waiting for the output, still waiting for it, and yeah, we're still waiting for it, and this will take a lot of time actually. So let's try out. Let's just try 40. 45 seems to be taking a lot of time. So let's try 40 over here, and even this too will take a few seconds. We're waiting for the output still, and yeah, there we go, we get it after a long period of time. I think that was like 7 or 8 seconds. So yeah, so you clearly see that this is not very efficient. A more efficient way of solving this problem would be to save the Fibonacci value at any position that you compute. So if you compute the Fibonacci value at a certain position, you save it in a data structure like a dictionary or something like that, so that eventually when you need that same value, when you want to refer to that same value, you can quickly refer to it instead of computing it again in the Fibonacci function. So then that trick is also known as memoization. It's part of dynamic programming, but I won't go too much into it because it's not very relevant to our course. So yeah, with that knowledge, we've talked about recursion. I'm going to go through one more problem, and that'll be in the next section. Our second recursion problem deals with counting to a certain number. So given the input 7, I want the program to count to 7. So it should output 1 and then 2 and then 3 and then 4 and then 5 all the way up to 7. So to create this, I'm going to use the function count to num. And a very simple approach, which is the iterative approach, and it's pretty simple to understand as well, is to run a for loop. Now, I hope you might be familiar with for loops. So in a for loop, you say for I in range num plus 1 in fact, because the bound is not inclusive, it's exclusive, so we need to add by 1, and then I'm just going to print I. So that should work, and if I run this, let's call this function as well. I'm going to say count to num, count to let's say 10, and let's run this, and you see we get 1, 2, 3, 4, 5. In fact, I don't want it to be from 0, so I'm going to say 1 to num plus 1. And let's run it this time. You see we get 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that's the iterative way of solving this problem. Iterative way, I couldn't say that before. It's the iterative way of solving this problem. Now let's come to the more complicated and to understand recursive way, but hopefully it makes sense to you after this section. So over here, I'm going to create the same function, count to num. This will take an input parameter num. And we want to use a recursive way to solve this problem. Now, bear with me while I code this up. I'll explain what it all means. So first I'm going to check if the number is greater than 0. That's the first thing I'm going to do. And if it is greater than 0, then I'm going to count to num, calling the function again with num minus 1. And then I'm going to print the number. And finally, I'm going to count to num, let's say 10. Let's run this. And you see we get the same output 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So, okay, what does all of this mean now? In fact, to make it more simple, I'm going to use the number 2 first. If you understand this, you'll understand it for any number. So let's run this again, and the output should be 1 and 2. 1 and 2, as you can see over here. So we start off with count to number 2. We give that as an input. The number is equal to 2. And in this case, the number is greater than 0, 2 is greater than 0. So then we count it up again. So we say count to num minus 1. At this stage, within this loop, num, what is num equal to? Num is equal to 2. But we're counting to num, count underscore 2 underscore num, 2 minus 1, which is 1. So now recursive function, we again count to num, we go back here, is 1 greater than 0? Yes, 1 is greater than 0, and in this situation num is equal to 1, and now we count to num to 0. Okay, bear with me for a second. So num equals 1, and then we count to num, we count to 0 because 1 minus 1 is 0. Okay, now we count to num to 0, we enter this function again, is 0 greater than 0? No, it's not greater than 0. Then we're gonna exit. Now over here, we come back to this original situation where we had num equal to 1 and count to num 0. Well, count to num 0 just returned, it just exited the function because num was now greater than 0. So now we have processed line 3. We move on to line 4. What is num equal to? Num is equal to 1 at this point, so it prints 1. Okay, we get now num is 1. Now in the previous situation, remember, num was 2 and count to num was 1. So after we process this num and after we exit this function, we go back to the original position when count to num was 2. Num was equal to 2 and count to num was 1. This line was processed just like before, and num is 2, so we print 2. So print 1 and then print 2. It's difficult to understand initially, but essentially what it's doing is it's counting, it decrements, so it goes from count to 1. So in the scenario where the count to num is 10, we go from 10 to 9 to 8 to 7 to 6 to 5 to 4 to 3 to 1 to 0. When we hit 0, num is not greater than 0, and then we go back to the position count to num is 1. Now Then we go back to the position where we print num and then count num is 1, and we go all the way up. So while count num decreases from 10 to 0, the printed output goes from 1 to 10. So that's how recursion works. It's definitely a much more difficult way of counting to a certain number, but hopefully it makes sense to you now. After these two recursion problems, I encourage you to revisit the pre-order and post-order functions that I talked about in the binary tree. And after we've understood all of that, it's time to move on to the next section of the course. So I'll see you there. So in this section of the course, we'll start by building our Lexer, which, as I've talked about in the previous few sections, decodes the input string. So let's say we give the input expression 5 plus 3. This is a valid expression, a valid input expression, because our programming language should be able to do basic arithmetic. So given this input, the Lexer or the tokenizer should be able to do lexical analysis and convert this into a list of tokens, 5 plus and 3. It should ignore any spaces like that. And yeah, that's the basic functionality of our Lexer. When we are making our programming language more extensive, we're trying to include more functionality like strings or assignments, variables, if statements, while loops, and all of that kind of interesting stuff. When we're doing that, we'll have to update our Lexer constantly. But for now, I'm going to create a Lexer that will be able to process these numbers and these operations, plus, minus, multiplication, or division. So for that, I'm going to create a class called Lexer. And this class will have the init method. It will take in self, which is the instance, and it will take a second parameter, which is the input text. Now over here, I'm going to set text equal self.text equal to text. Essentially, when I create the Lexer, so if I do Lexer equals Lexer, and I give an input expression 5 plus 3, I'm assigning a property called text to self being the instance itself, and the value of that property will be equal to the input given over here, which is 5 plus 3. So that's what I'm doing with this line, self.text equals text. Now the next thing I'm going to do is I'm going to create a variable called idx and set it to 0. Idx is the index of because when we're creating the Lexer, we'll have to iterate through each item of this. There's an input string over here. We'll have to go through each character, and to keep track of which character we're currently on, I'm going to use this idx. It's initially going to be 0 because indexing starts from 0. So if the 0th index of the string is equal to 5, the first index is equal to the spacebar, second index is this plus symbol, and so on. Now I'm going to create a variable called tokens, and that will be just an empty array where we will store all of our tokens. Now after that, I'm going to set the current character char, and that will be equal to the tokens. That will be equal to the text idx, self.idx. So initially the current char will be the number 5, the current character will be the number 5. Then we'll have to create a function called move, which will move to the next idx. It will increment the index, and once the index is incremented, it will update the character. The character will be this. So the character keeps track of self.char keeps track of the current character. And after that, I'm going to create one more property, and I'm going to say self.token is equal to none, and this will be the value of the current token, and you'll see what this means in just a few minutes. So after we've created the init method, I'm going to create a method called tokenize, which will convert this input text into the output tokens, and this will take in self as usual. Now to iterate through each character of this string, I'm going to use a while loop, and I'm going to say while the index is less than the length of the text. Let's just do print self.index for now. And if I run this, and if I do lexer.tokenize, and if I run this, you see, okay, so I forgot to increment it. So let's just increment over here. And if I run this, you see we get 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So we're going through each index of this input expression. So let's remove all of that for now. And now the first check I'm going to do, so there are two data types as of now. There's the number and there's the operator. Now a number can be composed of multiple digits. It can be this as well. Even this is a valid expression. So a number can compose of a string of digits, a combination of digits. So one or more digits, that's what defines a number. So if we encounter a digit, so if the current character is a digit, now how do we check if it's a digit? I'm gonna have to store all of the digits that exist. Let's say self.digits equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are all the digits. And then I can check if the current character is in self.digits. That means if it's 0, that's in self.digits. If it's 7, it's in self.digits. If it's 8, it's in self.digits. Now, a better thing to do is, since self.digits, the digits that exist, is universal, it doesn't change for each Lexer that we create. So a better thing to do is make this a class variable instead of an instance variable. So over here, I'm going to create digits. And I'll just copy the string over here. Let's paste that. Let's remove that line. And I'm going to do, instead of doing self.digits, I'm going to do Lexer.digits. So if the current character is in Lexer.digits, for instance, the first character is 5, it is in Lexer.digits, then I need to extract the entire number. The token is not just the number 5, the token is the entire number 5885. So we need to create another method that upon facing a number, upon facing a digit, this method will extract the entire integer, the entire number. So to do that, I'm going to say the current token, self.token, which is set to none, I'm going to make it equal to self.extract number. So let's create this method over here, extract number. So this extract number, if the current character is in digits, like over here, it's the number 5, extract number will extract the entire number, 5885. So to do that, we're going to first of all store the number as a string. And then while the current character is in self.digits, Lexer.digits, my bad, because this is a class variable. And that's it for now. And also I want to ensure that we are still within the text, so we're not, the index is not greater than the length of the text, and self.index is less than the length of self.text. If this is the case, then I'm gonna add the number, add the current character to the number. Now how do I increment the index? So okay, so when we hit the digit, we call self.number as self.extract number, and then 5, the current character is 5, so that will be added to the string over here, and the string will be 5. Now how do I increment the index? I can't just do self.index plus equals 1, because I then also have to update the current character. So I can do self.character equals self.text self.idx, so updating it. But this is a common functionality. We'll have to do this a lot of times. We'll have to move a lot of times. We'll have to move to the next character a lot of times. So to move to the next character, I'm going to create a method itself. Let's call it move. And I'm going to say self.idx plus equals 1. And if the self.idx is less than the length of the text, then I'm going to increment, then I'm going to update the value of the character. Set that to self.text at the index position of the updated index, which is plus equals 1. So whatever the index was before, now it's incremented by 1, and the character is the next position. So instead of doing this, I'm just going to call self.move. So that's our while loop essentially. We still have to detect floating point numbers which have decimal points in them, but we'll talk about that in just a few minutes. So as of now, I've set the number, and then I can't just return the number over here, because remember, we want to store tokens. Tokens have two aspects to them. They have the value and the type. So now the type over here is an integer and the value is a number. wouldn't it be better if we had a different class itself for the token, where instead of returning number, I can just return the token itself and give in the number and the type, let's say integer, and that's it. That's all we return, and the token class handles the rest. So for that, I'm going to create another class. Let's call it token, and I'll remove this over here. Let's create class token. And over here, we're going to have an init method. This token class will have a value and a type. Let's do type first. That makes more sense. And over here, I'm going to say self.type equals type. Self.value equals value. And I'm going to do one more thing. Instead of returning a token, I'll just return another class, which is the class of an integer. So I'm going to create a class called integer, and this class will inherit from the token class. So, and I'll pass over here. So instead of returning the token, all I'm going to do is I'm going to return the integer itself, the integer class itself. Now, why am I doing this? Because the first of all, integer, floating point, strings, and all of these numbers inherit from the base class token, because all of them have a type and a value. So that's why I'm doing the inheritance. And why I'm creating all of these subclasses, the integer, float, strings, is because these subclasses may have their own methods. Like for instance, the integer class may have methods like converting an integer to a float. The float class may have a method to convert a floating point number to an integer. So these classes will have their own custom methods. If we have a class of a string, which we will create later on, this class string will also again inherit from the token, and this class string may have its own additional functionality. Like for instance, you have to concatenate two strings. So we can write the method for concatenating two strings inside this class itself. So that's why it's better to create these classes and have them inherit from the main token class. Now, if I use the integer class over here, I'll have to pass the type and the value. So the value will be number and type will be integer, like that. Now a problem with this is that even though I've defined the integer class, I still have to pass int, and that will always be the case. So this is a form of code repetition. How about I just pass the number and the integer class manages to do the rest? So for that, I'm going to use the super function. So I'm going to call the init method again. And this will take in just one parameter, the value. And in the integer class itself, I'm going to hard code the value int as the type. So I'm going to do super, which is the token class. Now in the token class, I'm going to call the init method. And the type will just be integer and the value will be whatever is passed over here. So what am I doing with this? I'm saying, okay, extract number, and I'm going to return a type integer. The value of that integer is number over here, which we extracted. That is the value of this integer. Now over here, when the init method is called, when we create this class, or when we create this object, the init method is called. And in this init method, the super class's init method is called, which is the token class. And here we assign type as int and value as value, which is whatever is given over here, instead of passing in int every single time we create an integer, which is a form of code repetition and is not very efficient. Now let's try and handle floating point numbers as well. Now let's try and handle floating point numbers as well. So a floating point number will have a dot in them, a decimal point in them. And so I'm going to first create a check, is float as false? Because whether it's floating or not will depend on our output. If it's a floating point number, we'll return a class of a float. We'll return the float object. And if it's not a floating point number, we'll return the integer object. So over here, is float is false. And if the current character is in digits, or self.char is equal to a decimal point. So this is possible as well. And if this is the case, I'm going to say if self.char is equal to a decimal point, then I'm just going to do is float equals true. And I'm going to add the current character as usual. And now over here, I'm going to return the integer class if is float is false. That means if not is float. This is a way of checking if is float is false. If not is float, I'm going to return an integer. Else, if isFloat is true, that means the number is a floating point number. Then I'm going to return a class of float and give a number. And now let's create the same class again. I'm going to create a class of float. And the data type over here, let's do FLT, standing for float. So that's integer, that's float. What next? Now in the next part, we have to also talk about operations. So as of now, arithmetic expressions, we can input numbers, we can input operations. So we need to deal with operations as well over here. So I'm going to do elif the current character in Lexer dot operations, and let's store operations over here. Operations is equal to plus, minus, divide, multiply. So over here, let's say self.token. Since these operations don't span for multiple characters, like the digits, they spanned for multiple characters. You had 5, 6, 7 or 6, 7, 8, 3. This spanned for multiple characters, 6, 7 and 8, 3. But the operation is just one character, so we don't need to call an external method over here. All we can do is say self.token is equal to, first of all, we need to create the operation class, but the value will just be equal to the current character. So now let's create the operation class. This will inherit from the token class as usual. Self and value. Now let's call super. And in the init method, I'm going to pass operation op. And the value will be whatever is passed. So now I think this is pretty much it. Let's try and run it and see how it works. Actually, one more thing I forgot to do is I forgot to return the token from the tokenized class, from the tokenized method. So let's go ahead and return self.token, and now let's see if this works. So I'm going to run this and I'll create a shell, in fact a shell.py, and the shell.py will be used to interact with our programming language using the terminal over here. So first I'm going to import from the Lexer class. I'm going to from Lexer import Lexer. Then I'm going to say tokenizer is equal to Lexer. And over here I'm going to run a while loop, essentially taking an input expression indefinitely until the user quits the program. So while true, tokenizer equals Lexer, and we need to take an input expression. So let's say text equals input shadow script. That's the name of our programming language, if you remember. So this is the input we're taking. We will pass that input as a parameter to the Lexer object, to the Lexer class. And over here, I'm going to do tokens equals tokenizer dot tokenize. And let's print the tokens. So if I run this, and let's do 1 plus 1. Okay, so it's still indefinitely present over here. I think I made a mistake. I did not move after the operation. So over here in the extract number method, I moved to the next character, and that we don't need to add another move. We don't need to call move over here again after line 15. But in Lexer.operations, I did not do that, so I'll have to do self.move again. And now let's run this, see if it works. I have to quit the program first. And let's run, let's do 1 plus 1. And okay, another problem here. We don't have to return self.token, we have to return self.tokens. And over here in the while loop, after we've received the next token, I'm going to append to the tokens list. So append self.token. So hopefully now it makes more sense. Let me just recap. We run a while loop, we extract the token. The token can either be a digit or an operation. And once we find that token, we append it to the self.tokens list, and then we return self.tokens. So now let's run it. Hopefully it works this time. If I run and do 1 plus 1, okay, we get a list, and these are the classes over here: integer, operation, and integer again. Now this is an ugly way of looking at the classes. So I'm going to use another special method called the representation method. And I actually forgot to talk about this in the object-oriented implementation, object-oriented programming implementation. But essentially what this does is if I print the class itself, the representation will be printed. So now when I print the class, I get this ugly representation, but I can customize that representation using the REPR method, and the representation will just return the current value in the self.token class. And since all of these subclasses inherit from that, these two will have the same representation. So let's run it again. If I run it now and do 1 plus 1, you see we get the tokens 1, plus, 1. Now a problem we'll hit is if we use spacebars. So if I do 1 space 1, we haven't dealt with spacebars. We haven't told the program how to process spacebars. So if I run this, we'll see that we don't get any output. So to handle this issue, I'm gonna create a list of stop words, and stop words are just chunks that you ignore because they're irrelevant to your program. So over here I'm going to create stop words, and for now the only stop word will be a spacebar. So over here I'm going to say elif self.character is in lexer.stopwords. In this case I'm going to move to the next character, and I don't want to append anything, so I'm just going to break out of this iteration and move to the next iteration. So I'm going to hit continue. So now if I run this again and now I do 1 plus 1, you see it still handles. If I have multiple spacebars, it doesn't matter, we still get the same output. So that's basically it. And apart from that, so that's basically it for the Lexer as of now. We've handled floating point operations as well. Even I can even do 1.2 plus 7.8, and that too will work. I can do 7.5 multiplied by 3, and that too will work. And you see our Lexer is working perfectly fine, and this is a good base template to work from. Now whenever we have to add additional functionality like variables, if statements, and while loops, all we have to do is modify these classes, modify the while loop over here, the contents inside the while loop, and we'll be done. So that's about it for this section. Hopefully you understood all of the code related to Lexer. And now we'll move on to the parser, how we can create a parse tree, how we can create a tree to represent these arithmetic operations. And then finally in the interpreter, we'll traverse through the tree and compute the operations. So for all of that and more, I'll see you in the next section. So in this section of the course, I'll be working on the parser, which will create a list representation of the binary tree. So you remember how we talked about list representations and binary trees in the theoretical aspects of how the parser worked. So it's good to just review that section. But just as a quick reminder, let's say we have the expression 1 plus 2 multiplied by 3. The parser will create a binary tree using just lists 1 plus, and then it'll have a nested list inside of it, 2 multiplied by 3. And this is effectively the list representation of the binary tree, where the following highlighted bit is the right subtree and this is the left node, and plus is the root node. So now let's create the class. I'm going to say class parser, and over here I'm going to define the init method, which will take in self and the tokens. And over here I'm going to say self.tokens equals tokens. Now one more thing I'm going to do, just like how we did it in the Lexer, I'm going to keep an IDX, and I'm also going to create a move method to keep track of our tokens. Previously in the Lexer we did it to track the current character. Now we're going to do it to track the current tokens. So I'm going to say self.idx equals 0, and then self.token equals self.tokens on the current IDX. Now let's define the move method as well. This will increment the IDX, and it's going to do if the self.idx, if the index is less than the length of the tokens, only then is it going to update the token value. So now let's go ahead and create the method for passing our tokens. So this will be the method pass, and this method will compute an expression. Now remember how we talked about non-terminals and the different types of non-terminals that we have. We have the expression, we have the term, we have the factor. So these are three non-terminals. And we're going to create three different methods to define the grammar rules for each of these non-terminals. So we're going to first of all return self.expression. This is like the highest non-terminal. We want to compute the expression. And over here, I'm going to define, first of all, let's define the factor non-terminal. The factor non-terminal is pretty simple. We're going to check if the token type is of integer or float. So I'm going to say if self.token.type is integer or if it's float. In that case, I'm just going to return the current token. So let's say the current token is the number 5. The factor will check if the number 5 is an integer, which it is. So then it's going to just return the current token, and that is the factor. Now the term is slightly complicated. Remember how we defined a term to be a factor multiplied or divided by another factor 0 or more times. So I'm going to first say the left node of this term, because right now, let's say the term is, okay, let's just take an example, 1 multiplied by 2. Over here, we'll have 1 as the left node, multiplication as the root node, and 2. So this is our list. So the list representation of this will be 1, multiplication, 2. And this is the term that we're talking about. Now, how do we construct this term? First of all, we need to extract the left factor. So I'm going to say left underscore node is equal to self.factor. Then we're going to move. And then we're going to say, as of now, I'm going to assume that there's only one multiplication, there's only one operator. But as you know, the factors can be multiplied or divided by each other 0 or more times. So it doesn't necessarily have to be 1. So I'm going to say self.move. So 0 or more times, so the term could just as well be a factor itself. So I'm going to first of all say output equals left underscore node. In the case where there is only one node and they are not multiplied to another factor 0 or more times. So it's just a factor itself. In that case, the output will just be the factor. But in the situation where the operation self.token of value is equal to multiplication or division, in the situation where the operation is multiplication or division, the output won't just be equal to the factor. Rather, the output will be equal to, first of all, we need to save the operations. I'm going to say operation equals self.token. Then I'm going to move self.move. Then I'm going to say right underscore node is equal to self.factor again. And in this case, now the output will be equal to this list. So how will we construct the output? It will be left node, operation, right node. So I'm going to say output equals left node, operation, right node. And now let's return the output. So I hope that makes sense. In the case where the term is equal to a factor, there are no multiplication or divisions. In that case, we'll just return output as the factor. But in the situation where there is multiplication or division in between the operands, in that case, I'm going to make output equal to the left node, multiplication, which is whatever the operation is, multiplication or division, and right node. And then we're going to return the output. And I'll remind you, we're not talking about multiple operations. So this cannot handle stuff like 1 times 2 times 3. It can only handle a simple expression like 1 times 2, where there are 2 operands and 1 operator. Now let's do the same thing for the expression. And in fact, I'm just going to copy this code because it's pretty simple too. It's pretty similar to the same code. And in fact, one more thing I forgot to do was to move after the right node. And why am I doing this? So that when I call self.term in line 25, instead of self.factor in the expression, the left node will be self.term. I don't need to move after this. So I'm just going to remove that self.move method that I'm going to call over there. In fact, I can do the same thing over here. I'm going to do self.move, or rather, let's just leave it like this. So whenever you're calling a factor, you have to move after that because all the factor does is return the token. But whenever you're calling a term, you don't need to call self.move because it is all self.move is already called in line 19 after the right node. So we don't need to call self.move in this situation. So that's it. That should work now. I just need to change this to plus or minus. And let me save this, and I'm gonna run shell.py. So let's run it. Let's do something like 1 plus 2 multiplied by 4. And okay, I have to call the parser first of all, so I'm gonna import. So there we go. Let's run it again. 1 plus 2 multiplied by 4. And okay, I think I made a small mistake over here. I forgot to change this to self.term. So let me save now and run it again. Hopefully it works this time. 1 plus 2 multiplied by 3, let's do 3. And in this case, you see we do get this list. So how does this work? Let's just go through it. Left node equals self.term. In this case, the term is just equal to a factor because there is no multiplication or division following it. So then the term is just equal to that factor 1, and that's what we store as the left node. Then we check for addition or subtraction, which is the case. Then we move to the operation, store the operation, and then we store the right node as self.term. And this time, when we compute the term, there is multiplication or division, and that's why the term returns a nested list. So this works perfectly fine. This is in fact how our binary tree will look like. Even if we do 1 multiplied by 2 plus 4, this is exactly how the binary tree will look like when we convert the Python list to the binary tree. But we haven't solved one problem, which is multiple operations. As of now, we're only checking if there's one operation plus. But let's say we do 1 plus 2 plus 3. You see we have a problem. It's not giving the appropriate output. So how do we solve this? I'm going to make two changes. First of all, I'm going to run a while loop. I'm going to continuously check if there's addition or subtraction, and I'm going to continuously check if there's multiplication or division. So those are the two changes I'm going to make, and one final change I'm going to make, and I'll explain what this means in just a second, is I'm going to do left node equals the following list, and I'm going to return left node. I'm going to do the same thing over here. I'm going to return left node and get rid of this output business and make left node equal to that. So let's quit and run again, and I'll explain what this means in just a second. So 1 plus 2 plus 3, you see we get 1, 2 plus 3. If I do 1 plus 2 plus 3 plus 4, we get the following output. Now, how did this work? So effectively, by iteratively changing the value of left node, every single iteration of the while loop, we're changing the value of left node and we're assigning it the previous value. But by doing that, we're effectively pushing down the left node of the tree. So let me construct the tree and show you how it looks like. So this is how our tree looks like, and by continuously updating the left node's value and assigning it what the previous subtree was, so by continuously assigning this, let's go through this one time. So let's try 1 plus 2 plus 3, and in this case we get the left node as self.term, and self.term over here is just the number 1, and then we run a while loop to see, okay, each time we look for a plus symbol, we store the operation, we move, and then we get the right node as self.term again. So this is 1 plus 2 is the list over here, left node operation right node, but we assign that value to the left node. So essentially that list itself becomes the left node, and then plus, and then the number 3. And by doing this iteratively and by going down the left node every single time, by reassigning the left node, we're creating the right tree, as you saw over here. So that's the basic process. To summarize again, in every iteration, we are updating the value of the left node and we're assigning it the previous left node, operation, and right node. So what we previously had, like over here, what we previously had was 1, comma, plus, comma, 2. Whatever we previously had, we assigned that to the left node itself, followed by plus, followed by 3. So that's the process we used to accept multiple additions, so that we can say, okay, now an expression is equal to a factor added or subtracted by another factor 0 or more times. Now we've dealt with the 0 or more times aspect to it. So that's the basic summary of parsing stage. And now let's move on to the next section, where once we have created the tree, we'll have to traverse through the tree. So we'll have to do post-order traversal, and for all of that and more, I'll see you in the next section. So before we move on to the interpretation stage, I made a few changes to our Lexer code. Instead of storing the tokens and the token types in the Lexer.py file, I thought that it would be better to store it as its own external file over here. And that's the same code, except for the fact that in the representation method, we return it as a string, because the REPR, and there's also another method called string, def__string self, and they are pretty similar. They have a few minute differences which I'm not going to go into, but they're pretty similar in nature. And so both of these methods return output as only in string format. They don't return integers or floating point numbers. So it's better if we clarify that over here and return it as a string itself. Although in the lexical analysis stage, we did implicitly define the number as a string and then pass a string over here. It's just good to explicitly define the output to be of type string. So after that change, let's move on to the interpreter.py file, where we will be creating our interpreter. So over here, I'm going to create the interpreter, the init method, and this is going to take the tree as its input. Just like how the parser took the tokens as its input, now the interpreter will take the tree as its input. So after that, I'm going to create a method called interpret. And the interpret method is responsible for computing our arithmetic expression. So as of now, I've not talked about brackets, how you can compute expressions like 1 plus 2 in brackets multiplied by 3. We haven't talked about these. We'll talk about that in the next section. But as of now, we should be able to compute expressions like 1 plus 1 or 15 minus 6 multiplied by 5, whatever. We should be able to compute expressions like this after the interpretation stage. So in the interpreter, we'll have to do post-order traversal. Now, if you remember how the tree representation looked like, let's say for an input 1 plus 2 multiplied by 5, the tree representation would look something like this. You'll have 1 over here, you'll have plus, and then you'll have a nested list 2 multiplied by 5. So that's how our nested list, that's how the parser creates a representation of the tree. And we have to now interpret this. We have to traverse through this tree. And how are we going to traverse it? Using the post-order traversal method. And if you recall, post-order traversal refers to the fact that you have to traverse through the left subtree, then the right subtree, and then after that you have to go to the root node. Now let's for a second assume there are no subtrees, and let's just treat the binary tree with 2 levels. So there'll be only 2 levels here. There'll be a root node, let's say A, and then there'll be B over here and C over here. So let's just treat it, that should be here. That's better. Doesn't seem right. Yeah, there we go. So let's just assume that the tree is pretty simple. It has 2 levels and there are no subtrees. In such a situation, how will we interpret it? So an example of an expression like this would be 1 plus 1 or 5 plus 6 or 5 plus 6 or something like that. So how can we interpret such a simple binary tree? So first of all, we have to go through the left node, then the right node, and then the root node. So to do that, in post-order traversal form, we'll have to first go through the left node. So left node, and in our tree, let's say we have the expression 1 plus 1. the tree would look something like this. So the left node will be self.tree, the 0th index, so the first position over here. That's the left node. The right node is equal to self.tree 2. So we are now traversing through the left node, then the right node, and finally we'll go to the root node, and we'll compute the root node by adding the left and right nodes. So let's say the operator is equal to self.tree1, and over here we can return compute binary. This we'll have to create a function for this, and self.compute binary. So given the left node, right node, and operator, this function will calculate the output and return it. So here we'll give a left node, operator, right node. So this is the left subtree, and a subtree which contains only one node as of now. This is the right subtree, and this is the root node. So that's our post-order traversal. Now let's create the method compute binary. So we'll take in the left node, so left, up, and right. Now remember, we can't do the following. So if this is how it will typically look like, so we'll say if the operation dot value is equal to addition, then return left plus right. So this is one way of doing it, but it will be wrong because right now the left token is a string. It's not, even if we do left dot value over here and right dot value, these token values are stored as strings. Remember, over here we stored the number as a string, and then we stored the data type, which is integer. In that we passed a string number. So we can't perform this operation right now. In fact, we have to convert the left or right values into whatever that data type is. Like for instance, if the expression is 1 plus 1, let's say, so when given the expression 1 plus 1, the first token will have a value of 1 and a data type of integer. So then we have to convert from a string to an integer. We need to convert that value from a string to an integer. So one way we could do this is we can say, okay, if left dot type is equal to integer, left equals int left, elif left dot type is equal to float, left equals float left, and then over here let's do if right dot type is equal to int, same thing. And you'll see now that this is pretty inefficient, and we'll come up with a better solution. But just to illustrate my point, let's go along with this. If right dot type okay, so after all of that mess, and it's really disturbing to see to the eye, but anyway, after all of that mess, let's do if operation dot value is equal to plus, then I want to return left plus right, and let's just handle this for now. So I'm gonna save this, and let's close this over here. Oops, I'm gonna delete this itself. Now I'm gonna call the interpreter, so I'm gonna say interpreter is equal to interpreter. This will take in the tree, and this should be small. So interpreter dot interpret. So then I'm going to say result is equal to that, and let's print this result. I'll save, I'll click on run, and let's do 1 plus 1. Okay, we get an error. Alright, so this should have been left dot value and not left. So left dot value, right dot value. And I'm purposely doing this to show how inefficient this way is. Right dot value. Okay, here we go. One more time. 1 plus 1, and that seems to be a problem. Okay, this has to be elif. Okay, my bad. Let's run this one more time and hopefully it works again. 1 plus 1. Okay, we get 2. Perfect. Let's try 5 plus 3, we get 8. But again, this is a very inefficient way of doing this problem. So how can we solve this issue where our task at hand is to extract the type of the data of the token, and then depending on that type, whether it's int or whether it's float, using that type we convert it to its necessary data, integer or float. So how can we accomplish this task? So the first thing we need to do is we need to extract the type. So I'm going to say left underscore type is equal to left dot type, and right underscore type is equal to right dot type. Okay, so now we've extracted both types. What next? So there is a function in Python called getAttribute, and to show you how this works, I need to create two methods before, and then you'll understand how this works. So let's say the first method is read underscore int, and just bear with me for a second while I do this, and it will take in a value, and this will return the integer of that value, and there'll be define read underscore float, and it will return floating point value. So there is a method, there's a function in Python known as getAttribute, and we're essentially trying to find a method within the self instance. The name of the method is the second parameter. What's the name of the method? It's equal to read. It starts off with read, then there's an underscore, but now we don't know what the latter part of it is. I'm going to say the latter part of it is equal to left underscore type, and I'm going to call it, and this seems like a lot, but it's actually not that much. Okay, so what does this mean? So over here I'm saying, okay, now left is equal to read underscore left underscore type. So if left dot type is, let's say, integer, it will find the method read underscore int, and it will call that method by giving the value of the token as a parameter over here. So okay, let's not complicate it first over here. So now I'm going to say get attribute, within this instance find a method read underscore left underscore type. So left underscore type is equal to integer, so find a method called read int within self, and once you found that method, call that method, and the parameter which is value with as pass in the value left dot value. So pass the value of left as a parameter to the read underscore int method or the read underscore float method, depending on what the data type of left is. And I'm going to do the same thing for the right as well. So get attribute self read underscore, and over here we're going to do right type, and the parameter I'm going to pass is the value of right, so right dot value. So there we go. Let's save this, and I'm going to try and run to see if it works. 1 plus 1, we get 2. Same output, but it's much more easier to look at and much more efficient code. So now with that sorted out, we have to again look at the interpret method, because we still have to figure out subtrees. Now if I do something like 1 plus 2 plus 3, you see this will start giving errors because we haven't found a way to deal with subtrees. So let's consider a subtree over here, an expression which has a subtree. So 1 plus 2 plus 3, what is the list? How will that list look like? So let's create it. So there will be 1 plus 2, and then after that plus 3. So that's how the list representation of the binary tree will look like. 1 plus 2 plus 3. So that's the representation. So until now we were assuming that every single node will be just that, will be a node, there won't be any subtree. But now a node can be a node can be a subtree as well. So how do we deal with such situations? The first thing we need to know is that if it is a subtree, it will have a type of list. Notice that this is not a subtree, this node is not a subtree, and that's why it has a type of integer. But this node over here is a subtree, and that's why it has a type of list. So we need to first detect whether a node is a subtree or not. So to do that, let's first do it for the left node, and I'm going to say if is instance. I'm checking if the left node is an instance of the inbuilt class in Python, the instance of the class list. So if it is an instance of the class list, then we know that we need to compute this nested list as well. And to do that, I'm going to use recursion. So how are we going to do it? I'm going to say left underscore node is equal to self.interpret, calling this method itself, and the parameter I'm going to pass is this nested list. So I'm going to pass this nested list to the interpret method, and it will treat this as its own separate tree. It's going to compute it, and that value will be stored in left node. And if there is multiple subtrees, it will go recursively down. This process is known as recursive descent parsing, by the way. And it's gonna, for every single time we have a new subtree within a subtree, it's gonna go to each subtree, compute it, and eventually it's gonna come to this higher level, this topmost node, which with an interpreted value. So once we interpret left node, we need to do the same thing with the right node. So I'm gonna say if is instance right node of a list. If it is a list, then I'm going to say right node is equal to self.interpret right node. So there we go. Those are our two evaluations, and now we can deal with subtrees. So I'm going to say evaluating left subtree, and this is evaluating right subtree. So we're done with both instances over here, and this is finally the root node operation. So with that done, it's time to run our code. Let's see if we run our code, what output we will get. But actually before that, we need to also modify our compute bin method, because as of now it's only handling addition. So we need to manipulate that as well. So I'm going to do elif op.value equals minus return left minus right. Elif, and in fact I'm not going to do return, I'm going to store this as an output because this is an intermediate representation. We still have one more piece remaining. So in fact I'm just going to store this as the variable output. So I'm going to say output equals this, output equals left plus right, output equals left minus right. Elif op.value is multiplication. I'm going to say output equals left multiplied by right. And finally elif op.value is division. I'm going to say output equals left divided by right. So, and we're going to return output over here. Not just yet. Let's keep this for now. So I actually figured there'd be one problem over here. Notice that the interpret method is not accepting a parameter. It's using the original self.tree as a default tree to work with, but we don't want to do that. In cases when there is recursion, I want to pass in my own custom tree, which is the subtree, and I want the interpret method to process that subtree, to process that nested list. So how can we do that? So I'm going to come up with a efficient way to do this. So instead of passing in the tree in the interpret method, which is one way you could solve this problem, rather I'm going to create a variable called tree equals none. And what this means is to say that if the interpret method does not get a parameter, it's okay, it's not going to throw an error, it's just going to set the tree parameter to none. And that's the first case over here when we don't provide a parameter. So in the case where it is none, if tree is equal to none, if tree is none, in this case I want to make self.tree, tree equals self.tree. So if it is none, we're going to make tree equals self.tree, and we'll be working with only the tree. We won't be working directly with self.tree. Let's remove that as well. But in the case when it's not none, like this situation where we are providing our own custom tree over here, in this situation when we're providing our own custom tree over here, like left node and right node, in these two situations it will be using that tree parameter that will be passed in line 36 and line 41. So I'm going to save this, and now let's go back to the compute bin method. So in this scenario, I don't want to return the output as a default Python integer or a floating point number. Instead, I want to return it as my own class. I want to return the integer floater operation, because that's the point of having our own data classes. So how can we do that? Now, if the output, if left or right are both type of integers, then the output will definitely be an integer. But even if one of them are a floating point number, then the output will be a floating point number. Like for instance, if left is equal to 2.5 and right is equal to 2, the output will be a float. If left is equal to 2 and right is equal to 2, the output will be an integer. And let's say if left is equal to 2.5 and right is equal to 2.5, the output will still be a float. So even if one of these numbers is a floating point number, the output will be floating point, else it will be an integer. So for this, I'm going to say return integer. And see, this is where separating the data as its own custom file makes sense, because now I can import from this file itself. So I'm going to say from tokens, import integer and float. So return the integer value of output if left underscore type, let's deal with those, left underscore type and right underscore type, let's say left underscore type is equal to integer and right underscore type is equal to integer. If both are integer, return the output as in the format of integer, else return the output as a float. So now hopefully this works. We have the compute bin method written up. We have the interpret method written up using postorder traversal. And if I run this entire shell.py file, let's see if it works. So if I do, let's start off simple. Let's do 1 plus 1, we get 2. Let's try 1 plus 2, we get 3. I'm going to do 1 plus 2 plus 3, we should get 6, which we do. Let's try 1 plus 3 times 2. And over here, it'll be 1 plus 6 rather than 4 times 2. It'll be 1 plus 6. So that should be 7, which we do get. And I'm going to try floating point numbers, 2.5 into 2. We get 5.0. Notice that even if one of the numbers is floating point, the output is printed as a floating point number. So there we go. Our entire function is working. I'll do one more test to see if it's working. And again, the output is floating point. So our interpreter is working, and for the first time we have a running program that can compute arithmetic expressions as an input. So this is a huge step now because we have our basic foundation laid out, and after this things get very easy. All we have to do is write down our grammar rules, compute, make modifications to the Lexer, the parser and the interpreter. I removed the parser. Yeah. So all we have to do is make changes to the Lexer, interpreter and parser, and we should be able to work with variables, if statements and all of that. So in the next section, we're going to compute variables. So for all of that interesting stuff, I'll see you in the next section. So quickly before we move on to variables, I also need to talk about left brackets and right brackets and how we can use them to change our order of operations. So over here in the operations, I'm going to also add in the pair of parentheses, which are valid expressions, which are valid tokens as well. Oops. Okay, there we go. So which are valid tokens as well. So now let's go to the parser. And over here, how will the grammar rule look like? The grammar rule will change just a bit. Remember when we said that the factor is, we said it was just an integer, 0, 1 or 2, whatever, it's just an integer. Well, now it can also be a left bracket and a right bracket followed by an expression inside. So, and the brackets can contain expressions. So to extract the expression, we can use the expression method now. So over here, I'm going to say if self.token.value is equal to the open bracket, and in this case, I'm going to say self.move to move to the next token, because the open bracket is not very useful. We move to the next token, which is the start of the expression. Then I'm going to say expression equals self.expression. So now we have extracted the expression, and with that extraction, now we can return the expression. So if I save, and now let's go to the shell, and I'm going to run this file. 1 plus 2 multiplied by 3 gives you 7. But if I now enclose this with a pair of parentheses, you see we get 1 plus 2 plus 3. 1 plus 2 times 3 equals 9. And we can even deal with multiple parentheses over here. So if I have, let's say, 1 plus 2 multiply by 4 divided by 6, we get 2.0. So now finally we are going to be able to work with variables, assigning variables, and again as usual now we're going to use the same pattern. We're going to start off with the Lexer, update update the parser, and then finally update the interpreter. So to do this, I'm going to first talk about the grammar rules that are involved. The first grammar rule involved is in terms of the variable is the fact that the declaration is going to be made by the keyword make. So like in stuff like JavaScript, you have let, you have var. In Python, you don't have a declaration as such, but in our programming language, ShadowScript, the declaration will be make. So it's going to be make and then the variable name, and then that's going to equal something, let's say 50. So that's going to be our grammar rule for creating a variable. So we're going to start off with make. So for that we need to accept these text-based inputs, we need to accept letters. So for that we need to first create a constant over here to check if there is a letter or not. Letters. So with that we have defined the letters. Now let's go ahead and in the tokenize method I'm going to say elif the current character is in Lexer.letters. So in this case there are two possibilities. The first possibility is that the letter makes up the declaration. The second possibility is that the letter makes up the variable name. So over here we need to ensure that we take care of both situations. So I'm going to say first of all we need to extract the entire word, be it the declaration, be it the variable name. So just like how we had an extract number method, I'm going to run an extract word method over here. So I'm going to say word is equal to self.extract underscore word, and let's create that method just below the extract number method. So over here I'm going to say extract underscore method extract underscore word, and over here I'm going to say the word is equal to an empty string for now, while the current character is in Lexer.letters, same thing as before, and the current index is less than the length of the text. In these two situations, if both are true, then I'm going to say word plus equals the current character, and then we're going to move to the next character. And at the end, I'm going to return the word itself. So over here, we have extracted the word, and after that, we have to check if it is part of the declaration. So let's create a list for declarations. I'm going to say declarations. As of now, it's just going to be one item, the make declaration. But if we intend to have multiple declarations, like in JavaScript, you have let and you have var, two declarations. So if we have multiple of these, maybe then we have to update this list. So for now, let's keep it as a list. And then I'm going to say if word in declarations, Lexer.declarations. In this case, I'm going to set the token type to a declaration. So we need to create that data type over here in the tokens.py file. I'm going to copy this init method, and the name of the type will be DECL, standing for declaration. So now I'm going to say self.token is equal to declaration, and we'll pass the word as the declaration, and let's import this in our Lexical.py file. One more thing we need to import is the variable class, and let's create that as well. It'll be the same as our previous classes. And over here I'm going to create a variable, and the name of this data type will be var, standing for variable. So now that we've imported the variable, and we can move on to the next situation. In the case when it's not in the declaration, so else I'm going to say self.token is equal to variable. And now we have the token stored, so I'm not going to run the rest of the stuff. Let's just print the tokens to see what we get. So if I print tokens, And one more thing we need to do is we need to handle equal signs. So over here we have the equal symbol. So that is another operation that I have added over here. So now let's run the file. Let's run shell.py, and I'm going to write make a equals 50. And you see we get the declaration make a equals 50. The tokenization process works just fine. So now I'm going to go back to the Lexer, and I think we're pretty much done with the tokenization process. Now let's go ahead to the parser, where things get a little bit complicated. Now we need to, okay, let's go to the parser now. So to handle the variable assignment part, how can we handle this? So we need to create a new method. I told you for every grammar rule we'll be creating a new method. And now I'll be creating the grammar rule for a statement. Now variable assignment is a statement. It's a type of statement. There will be other types of statements like if statements, while loops. There are different types of statements. But one type of statement is the variable assignment. So how can you handle these variable assignments? So for that I'm going to create a method called statement. If the first token, so if self.token dot type is equal to declaration, then this will be a variable assignment statement. But if the self.token.type is equal to integer, or if it's equal to float, or if it's equal to operation, like for instance we can have the left brackets, so if it's equal to operation, in these situations, in these three situations, I'm going to set the statement type to be equal to arithmetic expression. So now in this situation you have arithmetic expression, in this situation you have variable assignment. So the first thing I'm going to do is I'm going to call statement like so. Now over here in the declaration, I'm going to, once we know that it is a declaration, I'm going to move to the next token. Next token will be the variable name, and to extract the variable name, I'm just going to create a new method called variable. So I'm going to say left underscore node is equal to self.variable. And in fact, we can create a binary tree of this as well. So how will the binary tree of make a equals 50 look like? It looks something like this. So we have the equals operator, and then we have that connection, and then a, and let's do 50 over here. So that's the binary tree of a make a equal 50. So now left node is equal to variable name. So self.variable will extract the variable name. Then we have to move after that. And then the operation, we have to check if self.token.type is equal to operation, or let's just say if the value is equal to equals. In this case, I'm going to save the token. So I'm going to say operation equals self.token. And over here, finally, I'm going to do, after we save the operation, I'm going to say self.move, move to the next token. And then the next token can be any expression. It can be an arithmetic expression. It can be just 50, or it can be 5 plus 7 minus 3 multiplied by 4. So we need to extract that expression. So I'm going to say right underscore node is equal to self.expression. So finally, I'm just going to return the list. Left underscore node, operation. So now we've extracted the statement, and if it's not an assignment statement, I'm just going to do self return self.expression. So let's save, and I'm going to delete, and I'm going to run the parser now, just see how the parser looks like. So if I save this, and let's just run it to see if we get any errors first of all. Make a equals 12. And we do get an error. Okay, we haven't defined the variable. Let's just define that really quick. So here, the variable method, all it will do is it will first move, because right now over here declaration. Okay, so we have already moved from the declaration, now the variable method will check for it will extract the token. So it's going to say if the self.token dot type is equal to var, that means if it's a type of variable, in that case we're just going to return the self.token. So now let's check this. If I clear and run again, make a equals 12, we don't get any error. Even the tokenization is worked perfectly. Now if I print the tree, you'll see what I meant when I said order of precedence, how we computed and all about the trees, and when I talked about putting the expression within a nested list and the declaration in an outer list. So that's how it look like. So if I run this now and I say make a equals 50 and I run it, you see we get a equals 50 over here. And for now you can't see it, but let's do make a equals 1 plus 2 multiplied by 5. You see now this expression is in a nested list. It has higher precedence. It's computed first, and then after that the assignment works, because we don't want to make a equal 1 and then compute. We don't want to make a equal 1 and then compute the rest of that expression. That makes no sense. We want to compute the entire expression, and then whatever the answer of that is, we want to assign that value to the variable a. So now we've modified the parser, we've modified the Lexer, and I hope that makes sense. Now let's go on to the interpreter, where we will be storing the variables in a dictionary. So as of now, we can compute basic arithmetic expressions, and we have also deal with the code dealt. We've also dealt with the code regarding the tokenization and the parsing. So let's say I create a variable and I do make a equals 5. So as you can see, the parser and the tokenizer are working fine. If I do make a equals something like 7 minus 2, then it knows that it has to encapsulate 7 and 2 into its own nested list. So we've dealt with the parser and the tokenizer. Now it's time to move to the interpreter. But I realized just a few problems with our current code, and I'm going to fix them right now. The first problem I noticed is that in the Lexer, we are storing the variable and we're giving it only one value, but in the tokens, the type of the variable is just var. So effectively, we're not specifying the data type. So say for instance, it's a variable with data type of integer. So it's, let's say we make the statement make a equals 5. So then the data type is integer and the value is 5. But in this case, the data type we've kept it as var, which stands for variable, and the value we've set it as the variable's name. So that's problematic. We need to store three things over here. We need to store, first of all, the variable name. Second of all, the fact that it is a variable, so var. And third of all, we need to store its data type. Now, as of now, like for instance, let's take the example, make a equals 5. We have not computed the expression over here. So we don't know what the data type is. It could be a float, it could be a integer. So we don't know what the data type is. So initially what we have to do is set it as an empty data type. And I'm going to do that using a question mark. So how am I going to represent data type and variable? Well, I'm going to say var, and then I'm going to give a pair of parentheses, and I'm going to give a question mark because we don't know the data type as of now. So this is what we're going to set the data type to as of now. But later on in the interpretation stage, when we've computed the value, when we've computed this expression, we're going to replace that question mark with the actual data type. So that's the first change I want to make. And over here, let's go to the Lexer. And yeah, so that was the only change I had to make. So now the Lexer over here, it'll create variable from the word, and in the tokens.py file, it'll give the data type with var followed by a question mark over here. Now with that done, let's move on to the next step. Now since we have changed our variable over here in the tokens, we've created the type in such a manner, we've changed it. We cannot be checking for self.token.type to be equal to variable. Instead, what we can check for is if it starts with the three letters var. So we can use the starts with method, which is an inbuilt method for strings in Python. And this will check if the string starts with the three characters va and r. So similarly, I'll just find the other instances where we have created var, And as you can see over here, another instance. So I'm going to, instead of making it equal, I'm going to check if it starts with the variable. And that's it. So now that we've done this, and now that we've changed the tokens.py file and updated the interdependencies, it's time to move on to another file which is called the data.py file. Now the data.py file will be storing all of the variables in a class. So this class will contain a dictionary, and this dictionary will be keeping track of all the variables and their corresponding values. So for that, we need to go to the shell.py file, and we need to create an instance of the data.py file before the while loop. We can't keep it in the while loop, because if we keep the instance in the while loop, the data would refresh every single time we get a new input. But rather than doing that, we want to keep track of the previous inputs as well. So here I'm going to say from data import the class data, and I'll create it in just a second. And over here I'm going to say base equals data. So we're creating an instance of that data. So I'm going to create class data and set the init method like so, self, and we won't be taking any properties. The only thing I want to run the first time the instance is created is I want to create the variables dictionary and set it to an empty dictionary. So let's save that, and the base is also set. Now I'm going to uncomment the interpreter and pass the base as an input to the interpreter. So now the interpreter can deal with all of the data, so it can write to the dictionary when like the action over here initially was with addition and subtraction, the action was to add two numbers. But in this time, we'll have to deal with memory. We'll have to add to the dictionary. We have to interact with the dictionary. And for that, we need access to the base variable. And that's why we're going to accept that base variable over here. And we're going to interact with the base variable. We're going to interact with the dictionary, add variables to the dictionary, change the values of variables to the dictionary, and read from the dictionary. So I'm going to say self.data is equal to base. So that's it in terms of the interpreter. Now let's go ahead and write the code for the data.py file. So variable.value refers to the variable name. And now let's go ahead and let's go ahead and save the data to the self.variables dictionary. So I'm going to say self.variables, and in this the variable name is going to be the key, and the value is just going to be the expression. So that's it. We're done with the write method, and now we're done with the data class itself. It's time to move to the interpreter, where we have to save our data and sometimes even retrieve the data. Like for instance, so we have two tasks now. The first task is to save data. Like for instance, if we have an expression make a equals 5, we need to save the value of a into this data dictionary. And the second task is, if we have, let's say, another expression make b equal a plus 1, in an expression we need to be able to parse, we need to be able to understand the value of a variable. So in the parse.py file, we have to update our grammar to say that we have to update the grammar in such a way that that a factor can be an integer, it can be a float, it can be an expression within a pair of parentheses. Also, it can be a variable itself, so it can start with the variable itself. So that's the only change I've made to the parse.py file, and I've returned self.token if it is a variable. So this will just return the current token corresponding to the variable. So that's it in the parse.py file, and now we need to work with the interpreter.py file, modify it so that we can be able to create new variables and read from the data.py file when necessary during these expressions, during the computation of such expressions. So for all of that and more, I'll see you in the next section. So now in the interpreter.py file, I'm going to treat the equal symbol similar to a binary operation. There's a left part and there's a right part, and we have to do some action with the operation. The action being, we have to set the left hand side equal to the right hand side, and we have to save the data in the data.py file. So how are we going to do this? We can't make an elif and put it over here, because we'll face problems in line 22 and 23, because they are reading the data as floats or integers, but now these are variables. So before we hit line 22 and 23, we have to compute the variable assignment. So over here, I'm going to say if the operation of value is equal to an equal symbol. Now in this case, what I'm going to do is I'm finally going to update the in over here. I'm going to replace the question mark with the actual data type. Notice that the right type is already computed. We've already computed the type of the right hand side, which is the expression. So once we've computed the expression, like for instance, let's say the expression is make a equals 5. The right hand side is the expression. The type of that is already computed in write.type, and in write underscore type stores that in a string format. So over here, instead of the first thing I'm going to do is I'm going to update the variables type. So how am I going to do this? I'm going to say left.type. Remember, left refers to the variable itself, the token for the variable. So I'm going to say left.type, referring to here. So left.type, I'm going to update that left.type, and I'm going to update that to equal var, and then within the pair of parentheses, I'm going to put in the type of the right hand side, which is the expression. So if the expression is an integer, is the type of an integer, the type of the variable will also be integer. So over here, I'm going to set it to write underscore type. So there we go. That's the first thing I'm going to do. I'm going to update the left.type. And the next thing I'm going to do is I'm going to write to the data.py file. So how am I going to write it? I'm going to say self.data.write. And remember, we had two parameters, the variable and the expression. So the variable, we'll just have to pass it as is, so the variable token. And the expression, I'm just going to pass that as is as well. So the expression will also have a type of a token, because remember, in computing a binary, we return, so because these expressions are sublists, so even they have to be computed first. And in computation of a binary, we return an integer or a float, and therefore even the right expression is not just a number, it is a type of token, either of integer or either of float. So that's it. We're going to write the data to the dictionary in the data class. And once we're done with that, I'm going to test this. So we haven't completed task 2 yet, reading variables, but we have the ability to write to variables. So now let's see. And just to see if it works or not, I'm going to return something. So after we write, I'm going to return the read all. So I want to see the updated variables list, updated variables dictionary. So to do that, all I'm going to do is I'm going to return self.data.read underscore all. So let's save it, and I'm going to go to shell.py now, and I'm going to run this. So if I do make a equals 5, there we go. We have a dictionary. If I do make b equals 10, that too will work. This is the variable name, and this is not a number. Don't be deceived by it. That's just because we have set the underscore representation as a string of the value. It's not a number. Instead, it is the token class. It's the instance of the token class. It's the instance of the integer or float class. So that's how we can create new variables. Now let's learn how we can read new variables so that we can even parse expressions like make b equal a plus 1. So to do that, I'm going to go back to our interpreter.py file. And remember, we have made the exception of variables as factors. We've coded that part in the parse.py file. So now let's go ahead and do part 2. Let's handle challenge 2. In an expression like a plus 1, where we have to compute a variable, we need to create a new method to read from a variable. As of now, in lines 27 and 28, we can compute methods. We can compute an integer and a floating point number using these two methods which are highlighted. But we need to create a new method for reading a variable. So let's read var and self, and this will take in the ID. So when we're calling it, left.value corresponds to the variable's name. So ID is what I'm referring to as the variable's name. Now the variable itself is equal to self.data.read using this ID, because in this data.py file we assigned the variable, the variable name is the key, and the value we assigned it to be the expression, and the expression is an instance of the classes integer or float. So right now we have the variable instance of integer or float. Now we need to extract the type. So in integer the type is int, and in float the type is float. So we need to extract that. So I'm going to say variable underscore type is equal to variable dot type. So now we've extracted the type from that token. Remember over here we saved the token, and the token could be integer or float. Now using that value, I'm extracting the type of the token, whether it's integer or whether it's float. And now from the read underscore var method, I'm going to call read underscore int and read underscore float. So over here I'm going to say get attribute from this self itself. I'm going to say read, and I'm going to input variable underscore type as our variable in this string inside of here. So we're going to embed variable underscore type in this string over here. And so we now need to call it, and we'll call it using the variable's value itself. So what is the value of the variable? That is equal to variable. So over here, it's equal to variable dot value. Value corresponds to whatever that expression evaluates to. Type corresponds, so value corresponds to whatever that expression evaluates to. Type corresponds to the type of that expression, whether it's integer or whether it's float. So that's it. So now we have the get attribute function. We're calling the get attribute function, and from the get attribute function we're calling the read underscore int and read underscore float methods. Now I'm just going to return this, and hopefully this should work now. So if I save, and just one more change I need to do here, just one more change is in, let's look at line 33 and 34. Left underscore type in this case, let's say it's a variable over here. So what will left underscore type be equal to? It'll be var int. It'll be equal to var int, but the method's name is underscore var. It's not equal to var underscore var int. So how do we handle this situation? So I'm just going to say left type. We're going to make it equal to variable. The type will be equal to variable if the string starts with variable. So even if the type is this, I'm going to assign even if type is var int, I'm going to assign the type to be equal to var, so that when we reach line 34 and 33 and 34, read underscore var is called and not read underscore var brackets int. So this is what I'm going to do. I'm going to make the type var instead of var int or var float, whatever, if it starts with var, else it's just a normal number, and in that case I'm just going to return the type left.type. And similarly I'm going to copy this, paste it over here. We have to do write this time, and let's save, and hopefully it works this time. So now I'm going to clear everything. Let's test our program out. So I'm going to run it. Let's make a equal to 5. I'm going to make b equal to 10, and then I'm going to make c equal to a plus b. And there we go, c is equal to 15, and our program is successfully working. So that's all about variables, and next up we're going to talk about unary operators. I left this thing out during evaluation of arithmetic expressions, but now we're going to talk about unary operators. So for all of that and more, I'll see you in the next section. So unary operators are simply operations that occur on just one operand. So an operand is like a number. So a binary operation, remember, was 5 plus 2. That's a binary operation. The first operand is 5, second operand is 2. You have two operands and one operation. So 5 plus 2 is a binary operation. A unary operation is something like plus 5, or it's something like minus 5. So something like plus 5 or minus 5. So to handle such unary operations, I'm going to change the factor a bit. I'm going to modify this factor method a bit to accept even an operation. So a factor can now be equal to an integer. It can be equal to an expression inside a pair of parentheses. It can be equal to a variable. It can also be equal to an operation plus another integer. So over here, I'm going to do elif self.token dot value, or let's do type dot type. If it's equal to op, if it's an operation, what do you do in this scenario? In fact, I'm not just going to do operation. I'm going to because in the Lexer.py file we defined even the equal sign to be an operation. So rather than doing that, I'm just going to use plus and minus because those are the two possible unary operations you can have. So here, if it's plus, or if self.token type is equal to minus. In this scenario, I'm going to first store the operation. I'm going to do operator equals self.token. Then I'm going to self.move. And then I'm going to do operand is equal to self.factor again. So if it's an integer, it will just return self.token and we get the operand as, let's say, plus 5. Plus will be the operator, and then operand will be self.factor. We'll go back here and say 5 is an integer. So we get 5, and plus 5 will be the operator plus operand. Now finally, I'm going to return an array, operator, operand. Instead of using 3 items in one array, now we're going to have only 2. This is a unary operation, the operator and the operand. And we need to handle this special case in the interpret method. Over here, I'm going to say if the tree is an instance of a list. First of all, it has to be an instance of a list. So I'm going to say if tree is an instance of a list, and after that, and the length of the tree is equal to 2, which means it's a unary operation, only the operator and the operand. In that case, what I'm going to do is I am going to compute it. Now I'm going to compute the unary operation. I'm going to say return self.compute underscore unary, and the operator will be tree 0, operand will be tree 1. So let's define compute unary. This will take in self, this will take in left, operator, operand. And this should just return the operator upon the operand. So it should just do operator, or in fact, I'll do it in this way. I'm saying if operator is equal to plus, and this time we have to still check for value. If operator.value is plus, I'm going to return plus operand. And we can't do operand here directly because remember we still have to configure the left and right, the operand in the same way we configured the left and right values. And so I'm going to copy all of this over here. It can be equal to a variable as well, plus a for instance. So it's just going to be for the operand this time. Operand is equal to variable operand.type and operand.type again. So one final thing, I'm going to read operand again. Okay. So let's do operand and operand. So there we go. Now elif the operator dot value is minus. In that case, I'm going to return minus operand. So now let's run this function. So I'm going to say in this scenario return compute unary. So this should work. And one more exception is, let's say we just input a number like 1, or let's say we input a number like 2. We can't handle that right now because we are assuming there is a valid binary operation. There is an operation, but there is an exception where the user just does not have any operations, just one number inputted. In that scenario, I'm going to do elif, let's say elif not is instance of list. If it's not even a tree, in that case I'm just going to return the tree. So if it's not a list, like for instance, if the only input is the number 1, the input is the number 1, in that case our tree will look something like this. It'll just look like the number 1, but instead it's actually the integer class. So it's the integer class with type of int and value 1. So it won't be a list, it'll just be this one value over here. So if it's not an instance of a list, that means the user has just inputted the value 1 or the value 2, has just inputted the number. In that case, I just want to return that out because you don't have any operation to do. Else, if none of these are true, we are going to do our usual binary operation. So let's delete, and this is the unary operation, and this is no operation. So let's save, and I'm going to run the shell. If I do +5, I get none this time. Let's see where we went wrong. Let's print the tree actually, see if that's working. +5. No, even the tree is returning none. So there's a problem over here itself. Okay, that's not type. That should be value, not type. So that's my mistake. So I'm going to close this again, run it. I'm going to do +5. Okay, and now we get a proper error this time. Let's look at this, look into this one. Okay, so it turns out I made two mistakes. The first mistake is that I didn't store this as a type. This is actually the type, not the operand itself. And I'm going to run type again. And the second mistake I made was in the parse method. I did not store this as value. I stored this as type. So I wrote self.token.type instead of self.token.value. So let's save now, and hopefully it works this time. So if I run again, +5, we get the output as 5. Let's do -5. I get -5. I'm going to make a equal to 10. And then I'm going to do -a, and we get -10. So that works now. We've computed unary operations, and we've also handled the scenario where we have no operation. Like let's try no operation, just the number 1. We get 1 outputted. So now that we've computed unary, binary, and no operations, we're effectively done with arithmetic. We can do complicated arithmetic as well, and we can handle variables, we can store them, we can read from them. And now we've covered most of the basics. We have some additional functionality to add, but it'll be really easy now since we have the basic foundation mapped out. So now let's move on to the next section. So in this section of the course, we'll be talking about comparison operators and Boolean operators. Now, Boolean operators, we've talked about this way back in the start of the course, where we talked about logic gates, and we said that there are 3 main Boolean operators. That's the AND gate, the OR gate, and the NOT gate. So in programming as well, you require these 3 logic gates, you require these 3 operators, you require these 3 Boolean operators to perform logical operations. Like for instance, I can find an instance over here where we use the logical operation in Python itself. So it only seems logical to give these operators to your users who will be using our programming language, so for them to allow them to create more useful and logical code. So that's about Boolean operators. Comparison operators are stuff like greater than, checking if 2 numbers are greater than each other, less than, greater than and equal to, less than and equal to, if 2 numbers are equally then to each other. So these are the sort of checks that comparison operators do. And remember, all of this right down in the fundamental level is just a bunch of logic gates operating. And that's why I had talked about logic gates in the start of this course. So to manage these operators, first I'm going to talk about the Boolean operators. So we're going to first create a list of Boolean operators. So I'm going to say Boolean operators, or let's just do Boolean. And over here we're going to have AND, the second one's OR, and the third one's NOT. And after that I'm going to go to the tokenize method, and over here these are examples of words. So this will come in the Lexer.letters condition, and we first check if it's a declaration. If it's not a declaration, then we're not gonna immediately assign it a variable, but we're gonna check if it is part of the Boolean operator. So I'm gonna say if word in Lexer.boolean operators, Lexer.boolean, and then I'm gonna set token equal to class Boolean, and inputting the name of the Boolean operator. Let's create this class Boolean, and I'm going to call it. I'm going to call the init method inside. This will take in self value and super dot underscore init bool and value. So let's save that and let's import Boolean from the data types that we've stored. So after that, now we're pretty much done with the Lexer. Now let's move on to the parser. In the parser, instead of calling the expression method, I'm going to call another method called Boolean expression. Now, what does the grammar rule for Boolean look like? The grammar rule will be like something like this. So we'll have bool underscore expression, and that will just be equal to a normal expression, and then the Boolean operator name. Let's say and, it can be or, it can be not, and that's going to be in small case, and or not, and followed by another expression. So two expressions followed by the Boolean operator. So to implement this, I'm gonna create a new method. Let's call it Boolean expression. Boolean underscore expression self. So left underscore node equals self dot expression. Then while the current token, same thing over here, and we're doing a lot of copy pasting, so it seems logical now to assign this same boilerplate code, this basic code, as its own method, and then we call that method every single time instead of rewriting all of this code, which kind of gets a bit messy now. We've already done it thrice. So now after I create the Boolean expression and the comparison operator expression, I'll be wrapping all of this code highlighted over here. I'll be wrapping all of this code into its own new method, and we'll call that method using in the Boolean expression, in the normal expression method, in the term method, and so on. So over here we're going to call self.expression, and if the token type is of bool, that's it, that's the only check. In that case, the operation is self.token and self.expression over here. So let's save, and I'm going to check if this works in the parser itself. So I'm going to comment out the interpreter. Okay, it's already commented out, and I'm going to run this. Okay, I'm going to run the shell. If I run, and now let's do the Boolean operator 5 and 6. You see that works. Okay, it's only it did not work. So type bool, left underscore node is self.expression. So the token, it seems to be working in the token. The token seems to be working well. The problem comes in parse. Okay, that's because we haven't called bool underscore expression, my bad. So wherever we've called expression now, self.expression, wherever we've called that, we're going to replace that with bool.expression. So over here, I'm going to say self.bool underscore expression. So let's replace it. I think that's the name of our method. Yes, it is Boolean expression. So let's replace the first one. Second one, let it be like that. Third one, let it be like that. And let's replace this one as well. And this one as well. So there we go. I think, okay, there's one more remaining. So I think that's it. I'm going to save now. And I think it should work this time. So let's go to the shell. Let's run. Let's run again. And I'm going to do 5 and 2. That works. Let's say if I do 5 plus 3 or 7 plus 6, and these operations don't mean anything as of now. They only make sense when combined with the comparison operator. So over here you see we get 5 plus 3, or is the Boolean operator 7 plus 6. And notice I've given this lower precedence over the other operators. I want this to be done last, because that's how you do it. You don't want to do 3 or 7 and then the addition. That doesn't make any sense. You want to give this the lowest precedence. So now let's move on to the conditional operators. So I'm going to say conditional, or why do I keep saying conditional? It's comparisons, list of comparisons, and then the first one will be greater than, next one will be less than, third one will be greater than and equal to, fourth one will be less than and equal to. And to check if two things are equal, in Python it's done as equal, but in our programming language it's going to be question mark equal, because I think that makes more sense. we're checking if it's equal or not. So we use a question mark. So now we need to create another variable here, special characters, and only if the character is in the special characters do we check if it's in the comparisons list. So it's going to be greater than, less than, equal, question mark. So these are the 4 possible special characters. Now let's go over here and I'm going to say elif self dot character. Yeah, elif self dot character in Lexer dot special characters. In that case, I'm going to make the comparison equal to an empty list for now. Comparison operator, let's do comparison operator. And over here I'm going to say while self dot character is in Lexer dot special characters and self dot index is less than the length of the text. In this case I'm going to add the current character and then I'm going to move, and finally I'm going to say self dot token is equal to, this time it's not going to be a Boolean, it's going to be a comparison. So comparison, and we're going to feed in the comparison operator over here. Let's create that as well. Comparison, and I'm going to call this comp is the data type. So let's import that finally, comparison, save, and hopefully it works now. So I'm going to go back to the parse.py, and remember where in Boolean expression we called expression. Now we're going to call comp expression, the comparison expression, and comparison too is pretty similar. In a comparison, comp underscore expression, that's just equal to an expression greater than or equal to, less than or equal to another expression. You get the idea, all of the comparative expressions. So we add a pipe in front of each of them and all of them together and followed by another expression. So here I'm going to create one, define comp underscore expression. So we'll take in self, the left node will be self dot expression. And now we need to change this to make it comp underscore expression and comp underscore expression. Left node equals self dot expression, and while self dot token dot type is comp, same thing, I'm going to copy this and I'm going to do, yeah, that seems fine. Lastly, we need to return the left node, so let's return left node, and over here instead of calling expression I'm going to call comp underscore expression. Save it and let's try and running it. I'm going to do 5. Let's check if 5 is equal to 5 and 7 greater than 2. So it groups this first as expression and groups the second expression and checks and adding the Boolean operator between both of them. So for the interpreter, I created the following code. It's really messy, but essentially what I'm doing is the same as what I did before. If left is greater than right, I'm going to output 1, which stands for true. Else I'm going to output 0, and I'm going to continue for this for all of the binary operators except not. Now not, although is a Boolean operator, is a unary operator because it does not apply on 2 different operands. It applies on just 1 operand. So to handle not, we have to form a different mechanism over here. So in the parse.py file, I created not for the unary operator, and I said, okay, just as how we made plus and minus unary operators, I'm going to make not a unary operator and return the operator and self.boolean expression, just like how I did over here. So because you can also have an expression, not just a factor. Like for instance, you can have not 5 equals 5. So the expression is 5 equals 5 and not is the unary operator. And it actually turns out that even you can have the same thing over here. So instead of calling self.factor, I think it'll be more wise to call self.boolean expression over here itself. So there we go. Now we're done with the parser.py file. And one more change I did was I allowed for not. So as of now, we only call Boolean expression if the first token is integer, float, or operation. Now even if the first token is not, like for instance not 5 equals 5, so this is still an arithmetic operation that I want to calculate, and therefore I go into self.boolean expression. So that's the two changes I made to parse.py. Now let's go to the interpreter and handle the not keyword in the interpreter. So over here, it's a unary operation, but do note that I just realized this, that in the unary operation, the operand can be an expression. It doesn't necessarily have to be an integer. Like for instance, you can have minus 5 times 5. This is a valid expression. As of now, I only thought of the possibility of maybe minus 5. But it's not necessarily, the operand is not necessarily an integer or a float. It can be an expression as well. So to handle that scenario, I'm going to say expression equals cell a tree 1. I'm going to say if expression is an instance of list, that means it has a subtree in it. So if expression is an instance of a list, then I'm going to say expression equals self.interpret recursion again expression. So now instead of passing in tree 1, I'm going to pass in expression itself. So I'm going to save this now, and let's go up to the compute unary method. And over here, let's add one final unary operator. If operator dot value is not, then I'm going to return 1 if not operand is true, else I'm going to return 0. So let's save all of this. Let's go to shell.py and I'm going to run this now. I'm going to do not 5 equals 5. That means 5 equals 5 is 1, so not 1 should be 0, and that indeed is the output. Let's try something else. Let's try 5 equals 5 and 7 greater than 2. That turns out to be 0, yes, because 5 is equal to 5 and 7 is greater than 2. If I do 5 equals 5 and 7 less than 2, we'll get 0. But if I do 5 equal to 5 and 7 or 7 less than 2, we should get 1, which we indeed do. So that's all about conditional operators and Boolean operators. Comparison operators and Boolean operators. And we'll use these two concepts to form our if statements. And finally, in the end, we'll run a while loop as well. So for all of that and more, I'll see you in the next section. So in this section of the course, I wrote the code regarding the if statements. Now, before we go into it, let's just talk about syntax. So the grammar rule will look something like this. We have an if statement followed by an expression, and after that we can have the keyword do. So expression, and if the expression is true, then do a statement. So that's the rule for if statements, and also there can be if elif statements as well in this. So you can have, if the statement is not true, then you have elif, another expression followed by do, another statement, and this can go on and on. The elif statements can go on and on, and then finally at the end you can have an else statement followed by do and a statement. So that's the way in which we're going to create our if statement. Now I've already written the code for the Lexer and Parser because this stuff is pretty repetitive and I don't want to write it all again. So over here I've created reserved keywords as its own list. Now it has if, elif, else, and do. And in the tokens.py file, we've also created a class for reserved tokens. Now after that, I went into the Lexer, and apart from checking for Boolean values and declarations, I'm also checking if the word is in the reserved list. In that case, I'm going to add it to the instance of a reserved class. Now after that, I'm going to go to the parser. The parser has three aspects to it. First of all, in the statement method, we check if the token value is if. If it is if, then we go to self.if statements. We run the self.if statements method, and the self.if statements method runs over here. It stores the conditions and actions in two arrays. So the conditions correspond to these expressions stored in a list, and actions correspond to these statements stored in the list. So we store both of them as initially they're empty, and then we call if statement, make it self.if statement. Now we go to this method self.if statement, which is responsible for grabbing one condition and grabbing one action pertaining to one if statement or one elif statement. So it first of all moves from the if or elif statement. So it moves from the if or elif statement and goes to the condition, and then it stores the condition as a Boolean expression. Then if the token dot value is do, as we saw over here, then we grab the statement, we move up from the do, and then we grab the statement and store it as an action, and we return it. Now this second elif statement is for a special case when we have unary operations. Now when we have unary operations in parentheses, we call self.boolean expression within it and tend to move a point after the do keyword. So we tend to move ahead of this. So this second statement, which is over here, the second statement checks for if the do keyword is in the previous token. In that scenario, we return the condition and action. So that's the elif statement, and we run a while loop for all the elif statements. In the end, we check for an else statement. We move from the else statement, we move from the do keyword, and then we grab the action and store it in a list of 3 items. If there is no else statement, we store the output in a list of 2 items. Now let's go back over here. The final output will contain self.token, and that is used to, we are explicitly declaring if the statement is an if statement or not, because that makes it easy to detect the if statement in the interpreter. So that's what the self.token does in the first value, and self.if statements is just the output that we saw previously, the conditions, actions, and else action. Now let's go to the interpreter. In the interpreter, we have, okay, so yeah, over here in the interpreter, we check if the first value is reserved. We first of all check if the instance of the tree is list. Then we check if the first value is reserved, and then we check if it's an if statement. So we're using this first item over here. We're checking if it's reserved, we're checking if it's an if statement. In that case, we're gonna iterate through each condition in the conditions list, and we're gonna also store the index of our loop. Then we're gonna interpret the condition, and if the evaluation turns out to have a value of 1, then in that case we're gonna use the corresponding index and match the action using that corresponding index, and we're gonna interpret that action. Finally, if the length is 3, that means that there is an else statement. I'm gonna interpret that else statement. And even if both of those conditions fail, that means even if there is no else statement and the if conditions fail and the elif conditions fail, in that case I'm just going to break out and return. So that's pretty much it. I noticed one error I had made beforehand, is that in the compute unary method I've forgotten to return the output in the form of an integer or a float, and I updated that as well. So finally I'm going to go to shell and I'm going to run this. We can have expressions like if 5 is greater than 2, to make a equal 3, and you see we get a equal to 3, and this is in fact printing from here. So let me just delete this evaluation print. So let's control C clear. I'm going to do if 5 is greater than 2, do make a equal to 3. We get a equal to 3. If 5 is less than 9 or 7 is greater than 3, do make a equal to 6. We make a equal to 6. If 5 is greater than or equal to 5, do make a equal to 9. A becomes 9. If, let's see, if a is equal to 9 and 7 is greater than 3, do make b equal to a plus 1, and b becomes 10. So that's the if statement covered, and with that we have completed if statements, variables, and expressions. So in this section of the course I created the while loop, and first of all I modified the Lexer, and before we do that we need to think about the grammar rule, and this is how it looks like. It's similar to the if statement where you have a while, the while keyword, followed by an expression, followed by do, followed by a statement. So I just added while to the reserved list, and that's it to the Lexer. Now I move to the parser. In the parser, apart from the if statement check, I also need to check if it's a while statement, and I need to return accordingly. I'm returning a while statement over here, so self.while statement. So I move from the while keyword, I move to the expression, and then over here I store the expression as a condition. Then if the value equals do, if the next value is equal to do, in that case I'm going to move, and then I'm going to store the action, and then I'm going to return this list. And again, for that special case, when you're using unary operations, you kind of move ahead because you call Boolean expression within the factor method, and that's why I need to add this additional check over here. So that's it in the parser. Now let's move on to the interpreter. So the interpreter, remember we had the check for if the value is an if. Now let's check if the value is while. Then these are just some checks. All right, there we go. Now we check if the value is while. In fact, I don't even need this action over here. So then I store the condition self.interpret 310. That is the condition that we passed from the parser to the interpreter. Then while the condition.value is 1, that means while that condition is true, I'm going to do the action and print out the response. So self.interpret the action. Then again, I'm going to update the condition, because if I don't do this, the condition won't get updated. And I'm going to update the condition, and then again we're going to go into the while loop and check if the value is 1. So with those changes, let's go ahead and run the shell. So I'm going to click on run, and now let's do make a equals 0 while a is less than 10, do make a equals a plus 1, and if I run this, we get a equals 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and finally we get none printed out, so I don't really want that. So I'm going to go to the shell, and I'm going to say if result is not none, only then I'm going to print the result, else we're just going to leave it empty. So let's do make a equals 0 while a is less than 10, do make a equal to a plus 1, and that gives our correct response over here. And as you can see, it converts it to floating point numbers for some reason, and these are just some minute details that are a bit buggy in our code. It's not 100% foolproof. It's not as good as the modern programming languages, but the goal of this course was to teach a few concepts and create a simple programming language which can compute arithmetic operations and also some additional functionality as well.